The planet keeps its own record, and it keeps it in layers: mud that hardened, ash that fell and settled, the shells of small animals sinking through water for long enough to turn into stone. Most of the time it accumulates about as slowly as anything can, and still be accumulating, a few centimeters in a human lifetime in the places where it happens at all, and reading it is mainly a matter of counting downward and being patient. There are places in that record where the writing changes. They are not much to look at. Most of them are dark and thin, and if you walked past one in a road cut on your way somewhere, you would have no particular reason to stop. What makes them strange isn't how they look. It's that the same lines turn up everywhere: a hillside in southern Scotland, a quarry in eastern China, a gorge in central Italy, a core pulled up out of the ground in North Dakota. Different rock, different continents, whole oceans in between, and the same handful of bands in the same order at the same depths relative to one another every single time. Whatever put them there didn't happen to a place, it happened to the planet. 5 of those bands mark intervals when most of what was alive stopped being alive. The oldest sits at about 443 million years, at the end of a period called the Ordovician, when nearly everything on Earth still lived in shallow water and the land was more or less bare. The second comes in 2 parts, around 372 million and 359 million years ago in the Late Devonian. The third, at 252 million, closes the Permian, and it is the worst thing that has ever happened here. The fourth, at 201 million, ends the Triassic. And the fifth closes the Cretaceous 66 million years ago, and it's the one everybody knows. An object about 10 kilometers across, arriving off what is now the Yucatan coast. After the largest of them, the light went down, not for a season, for years, and in some cases very much longer than years. Sunlight cut, photosynthesis struggling, the whole biological output of the planet running at a trickle. In most of these events, the dying happens in the aftermath, in conditions like that, rather than in whatever started it. For about 40 years, these 5 have been ranked against one another. Which was worst, which was second, which was merely enormous. The ranking has an author and a date, and it appears in almost every textbook that covers the subject. It doesn't hold still. Change what you measure and the order rearranges itself. Count the proportion of species lost and you get one sequence. Count how fast they died, how much of the loss was compressed into how short a window, and the order comes out differently. Count how much of the structure of life came apart, the architecture rather than the names on the list, who eats whom and what builds the reef and what the seafloor looks like a million years later, and you get a third sequence, in which one of the 5 falls from near the top to below, an event that isn't even on the list. That one killed a larger share of the species alive at the time than almost anything else in the entire record, and left the shape of life on Earth very close to the way it found it. Which is a strange sentence to be able to write, and it means the question of which was worst depends completely on what that word is supposed to be measuring. Whatever the order turns out to be, something small got through all 5 times, on a planet that had just finished demonstrating it was under no obligation to let anything through at all. That is the only reason there's anybody here to argue about the ranking. If this is the kind of thing you want more of, subscribing does more for a channel like this than almost anything else. And in the comments, I'd like to know something. If you had to choose one measure, the number of species lost or the number of years the world needed to come back, which would you use? I have a preference, and I'm not at all sure it's the right one. Now, if you're settled, settle a little further. Whatever you're holding can be put down, and your jaw is probably doing more work than it needs to. None of this ranking came out of the rock, though. It came out of a filing system kept by one man over most of a working life. His name was Jack Sepkoski, and he taught paleontology at the University of Chicago. The work that took up most of his adult life sounds, described plainly, like clerical work. He wrote down when things appeared and when they stopped appearing. Not species. Species-level data in the fossil record is too patchy to trust at scale. He worked one level up, at the genus, the rank that gathers a handful of closely related kinds under a single name. For every genus of marine animal anyone had ever described from the fossil record, he recorded two things: the oldest rock layer it had been found in, and the youngest. Then he recorded where he had got that from, which monograph, which museum catalogue, which paper, in which language, by whom. By the time he was finished, there were about 37,000 of them. It is hard to convey how strange an object that is. 500 million years of ocean life, everything shelled, everything swimming, everything that burrowed or drifted or built a reef, insofar as it left a trace, and somebody found it and wrote it up, reduced to a first date, a last date, and a citation. One man, working through the published literature, turning the fossil record into something you could add up. And the reason it mattered is that once the record is a list of first dates and last dates, arithmetic becomes possible. You can ask how many genera were alive at any given moment, how many appeared in a given interval, how many vanished. The fossil record stops being a collection of objects and becomes a curve. The last revisions to his working file are dated to a stretch of 4 months in 1998. He died the following spring. The compendium the field still runs on was published after his death, edited into shape by other people out of a file that had stopped being edited. 16 years before that, in March of 1982, Sepkoski and David Raup, a colleague in the same department, took an earlier version of the data and did something very simple with it. They used families rather than genera, one level coarser again, and plotted the rate at which families were going extinct, interval by interval, across the last 540 million years. The first thing that plot shows is a slow decline. Extinction rates were higher early on and have drifted downward ever since, which is interesting in its own right and not what they were looking at. They drew a line through that decline and then drew a band around the line marking how much scatter you would expect if nothing out of the ordinary were going on. 5 points stuck out above the band. That is the whole of it. That is where the big 5 comes from, a paper in science, and 5 dots that a line could not account for. At the moment of its birth, it was not a claim about volcanoes or asteroids or the end of the world. It was a claim about scatter. It survived as a claim about scatter for roughly a year. In 1983, Quinn published a short paper pointing out a problem with the arithmetic underneath it. Drawing that band requires an assumption about how the extinction rates are distributed. Raup and Sepkoski had assumed the scatter was symmetrical, the ordinary bell shape, values falling about evenly above and below the trend. Quinn argued the distribution was log-normal instead, the kind of quantity that clusters low with a long tail running high. River floods behave that way. So do the sizes of cities. The consequence is not subtle. If the scatter is symmetrical, 5 values that far above the line are extraordinary and demand explaining. If the scatter has a long, high tail, then a handful of very large values is simply what the top of a tail looks like, and none of them needs anything special to have happened. Under that reading, none of the 5 stand out. The point did not go away. 20 years later, a study by Wang came at it from the other direction, using the genus-level data rather than families, and found no break in the numbers where ordinary extinction stops and mass extinction begins. The two run into each other continuously, which means the 5 largest extinctions in the history of life are not, as a matter of statistics, a different kind of event from the ordinary business of things dying out. They are the large end of the ordinary business. The term stayed anyway. Charles Marshall went back over the whole 4 decades of it in a review published in 2023, and his account of why is unusually blunt for a scientific paper. The Big Five survived, he writes, not because of any statistical argument, but simply because they represent the largest drops in diversity. They were demoted almost immediately and kept regardless, because the phrase was useful and everybody knew what it meant. The awkward parts are all still sitting there in the data. Marshall counts 6 further peaks substantial enough to be worth naming, scattered between the Carboniferous and the Pliocene. Older still, in the Cambrian and the earliest Ordovician, there are extinction events that were proportionally worse than any of the 5, and they are left off the list largely because of where the time axis happened to be cut. His own summary is that the choice of 5 is arbitrary enough that a person could make a defensible case for the big one or for the big dozen. None of which means the 5 didn't happen or that they were small. They are the largest losses of diversity in the marine record since the early Ordovician, and the physical events behind them are as real as anything in geology. What collapsed under Quinn's arithmetic was the category, not the events inside it. The idea that these 5 are a separate species of thing, cleanly divided from the ordinary rate of loss. There is a second episode from the same 2 men and the same data, and it says something about how much was being asked of it. 2 years after the 1982 paper, Raup and Sepkoski went back to the extinction peaks of the last 250 million years and found that they seemed to arrive at regular intervals, one about every 26 million years. Regularity on that scale is a serious claim because nothing on Earth keeps time like that. Whatever was doing it would have to be outside. Within a very short time, there were proposals for a companion star to the Sun on a long tilted orbit, swinging out every 26 million years through the cloud of comets at the edge of the solar system and knocking a shower of them inward. Somebody named it Nemesis. People went looking for it. They didn't find it, and the statistics didn't survive either. The fossil record is carved into time units of its own, stages defined by the fossils in them, and those units average a few million years each, feed a random scatter of extinction peaks into bins that size and peaks come out at roughly regular spacing whether or not anything is causing them. The clock was in the calendar, so the category is soft. The numbers inside it turn out to be soft as well, and in a way that is much easier to check. Almost anyone who has heard of the end-Permian extinction has heard that it killed 96% of marine species. It is one of the most reproduced figures in Earth science, and it comes from a calculation Raup published in 1979, working backwards from the number of larger groups still visible in the record to the number of species there must have been to fill them. In 2016, Stephen Stanley went through that calculation again and found 2 problems. The first is that it had been run on Middle and Late Permian data combined, and there are 2 separate extinctions inside that window, so the arithmetic was crediting the losses of both to one of them. The second is that no allowance had been made for ordinary background extinction, which carries on right through any crisis interval and has nothing to do with the crisis. Pull the 2 events apart, subtract the background, and the figure comes out around 81%, which is still a loss it is difficult to hold in your head, and which is also 15 points below the number in the textbooks. Stanley noted that the older figure had been quoted in the scientific literature more than 60 times since the mid-90s, and wrote, about as flatly as that kind of paper allows, that it should not be quoted even as possibly correct. His own summary of the corrected picture is worth having in his words. Life did not nearly disappear at the end of the Permian. Something like 90 orders of marine animals and more than 200 families came through it. Put those 2 things side by side, a category that is a convention rather than a boundary, and a headline number that moves 15 points when somebody checks the arithmetic. And the question this is supposedly about turns into a different question. Nobody can say which of the 5 was worst until somebody says what worst is measuring. And there are at least 5 reasonable answers to that, each producing a different order. You can measure how much of the living world was erased, the proportion of genera or species present before and absent after. Speed is a separate question entirely, because losing 80% across 20 million years and losing 80% across 60,000 are not the same physical event, whatever the totals say. A third measure ignores the casualty list and looks at the architecture instead, whether reefs still got built, whether food chains held their shape, whether the seafloor went on working the way it had. Then there is the length of the recovery, how long the world needed to reassemble itself, and finally, the part that never reassembled at all. 5 rulers laid against the same 5 events, producing 5 different orders. You have almost certainly been taught the number 5. There is a fair chance you have been taught the number 96 as well. Both are useful, and both are the residue of decisions about which time units to use, which level of the hierarchy to count, which data to combine, where to draw the band around a graph. That is not a complaint about the science. It is what science looks like from close up, where the judgment calls are still visible. But it does mean the order everybody has agreed on was produced by a series of those calls, and most of them are still open. The oldest of the 5 sits at the far left of that graph, 443 million years from the pen that drew it. On the page, it is an inch or so of paper. In the world, it was a shallow sea, somewhere warm, under a sky nothing had ever flown through, beside a shore that almost nothing had ever walked on. The water over that shelf was warm and shallow, and clear enough that sunlight reached the bottom of it, which is the whole reason anything was down there at all. Crinoids stood across the seafloor in beds, animals on stalks, anchored at the base, filtering the current with arms like feathers, thick enough in places that anything swimming through would have been pushing through a meadow. Brachiopods lay half-buried in the sediment between them, shelled creatures that look like clams and are not related to clams in any close way, in numbers that are genuinely difficult to picture. Trilobites worked the mud. In the warmer patches there were reefs, built by corals and by sponge-like animals that no longer exist anywhere on Earth. And drifting through the open water above all of it were colonies of small, soft animals whose flattened fossils look so much like pencil strokes on stone that when people first found them, they were named for handwriting. All of it was in the shallows. That is the single most important fact about the Ordovician Ocean, and it is an easy one to slide past. The deep sea existed and had things living in it, but the overwhelming bulk of animal life on this planet was gathered into a thin, sunlit band, a few tens of meters thick, laid over whichever parts of the continental crust happened to be underwater. Above the waterline, there was almost nothing. Low mats of something plant-like in the damp ground, possibly a few small arthropods at the edges, and otherwise bare rock and sand and river gravel to the horizon. The rivers ran without banks in the modern sense, spreading and braiding across open gravel because there was nothing growing anywhere to hold a bank together. And the continents were in the wrong places. Gondwana, the enormous southern landmass that would eventually come apart into South America, Africa, Antarctica, Australia and India, sat squarely over the South Pole, and the part of it lying directly on the pole is now the Sahara. The rest of the land was scattered through the tropics in pieces, with the sea flooded well up onto them, so that much of what is now the interior of North America lay under warm, shallow water. Then ice began to grow on Gondwana. Not quickly and not all at once, but the way ice sheets do grow. Snow that fails to finish melting one summer, then fails again the next, then goes on failing for long enough that the buried layers compress into something dense enough to flow under its own weight. North Africa went under an ice sheet. There are grooves cut into the bedrock in Algeria and Libya, running in the direction the ice moved, and sitting on top of them is the rubble it dropped when it finally let go. Ground rock flour and boulders carried in from somewhere else, and nothing sorted the way water sorts things. The water to build an ice sheet has to come from somewhere, and there is only one place it comes from. Sea level fell by something like 100 meters. 100 meters sounds like a statement about depth. On a continental shelf, it turns out to be a statement about area. Shelves are close to flat. They slope away from the land at a fraction of a degree, sometimes for tens of kilometers and sometimes for hundreds, and then they reach the shelf break, where the floor tilts over and drops steeply into deep ocean. Take 100 meters off the top of an arrangement shaped like that, and the shoreline does not move 100 meters. It travels outward across the flat until it finds the new waterline, which on a gentle enough gradient can be a very long way indeed. Everything that had been living on the drained part is now standing in air. The shallow seas that had flooded the middles of continents came off, worse still, because they were perched on continental crust well above the level of the shelf break, with nowhere downslope to retreat to. They did not migrate, they emptied. What survives an adjustment like that is a narrow strip of shallow water clinging to a steep slope. The shallow water living space of an entire planet, which had been spread over an area you would have to measure in millions of square kilometers, was compressed into a fringe. The cold was doing its own work alongside the geometry. The world lost something like 9 degrees, and for animals whose entire evolutionary history had taken place in warm, tropical shallows, that is not a question of discomfort. Shelled marine invertebrates tend to have narrow tolerances. The tropics stopped being tropical, and there was nowhere warmer to go. The whole of that first phase ran for about 340,000 years. 9 degrees, 100 meters of water, and the draining of most of the shallow sea on Earth spread evenly across 340 millennia. Species were disappearing at something like 8% every 100,000 years, fast by geological standards and almost entirely undetectable by any other. If you had lived 80 years on that coastline and watched the tide marks with real attention your whole life, the sea would have gone down by roughly the width of a finger. Your grandchildren would have found the same beach in more or less the same place. Nothing about any of it would have looked like an ending. That is the particular unpleasantness of this first phase. Nothing broke. There was no catastrophe to point at, and no afternoon on which anything went wrong. The habitat drained at the speed water drains out of a very large and very flat basin, and the animals living in it gradually ran out of places to be. Why the ice came at all is a good deal less clear, and it is worth being straightforward about that. Cooling on that scale requires carbon dioxide to leave the atmosphere, and there are 3 plausible ways it could have gone. A mountain range was rising along the eastern edge of what is now North America, and freshly raised rock weathers quickly, and the chemical weathering of silicate rock pulls carbon out of the air and buries it in the ocean. The first low mats of land vegetation were spreading at roughly the same time, and they seem to have sped up the weathering of the ground they grew on, achieving the same result by a different route. And there was volcanism. Big eruptions leave a mercury signature in marine sediment, and rocks of this age from South China and from North America carry mercury spikes in the right positions. None of the 3 has won. Harper's review of the whole problem, published in 2023, works through the evidence carefully and then says plainly that no clear consensus was reached about the overarching cause. There is a harder version of the difficulty as well. In 2020, Bond and Grasby published a paper in Geology whose title sets out the position without any decoration at all, that the late Ordovician mass extinction was caused by volcanism. warming, and the loss of oxygen from the ocean, and not by cooling and glaciation, which is an uncomfortable thing to sit with, having just walked through the ice. I don't think the geometry is wrong. The sea did leave, and the animals that died were the ones living in it. But there is a serious argument that the ice was a symptom of something larger rather than the engine of it, that the real machinery was somewhere else entirely, and the people making that argument are not cranks. What is not in dispute is what moved in afterwards. Across shelf environments worldwide, in the interval after the first phase of dying, the rock records the same small group of brachiopods. Cold-tolerant, unfussy, poor in variety and staggering in quantity. And the striking thing about them is that they are the same everywhere. The same handful of genera turn up in Wales and in South China, and along the edge of what is now Canada. Paleontologists call it the Hernantia fauna, after the genus that appears most often, which is itself named after a valley in North Wales where rocks of that age were first properly described. It is one of the most widely distributed and shortest-lived assemblages of animals anywhere in the fossil record. A world in which the same few species turn up at every location is a world that has been simplified. The variety that characterized the Ordovician shelves, the local specialists, the reef builders, the things that only worked in one particular kind of water, had thinned out badly, and what held the territory now was a small number of generalists that could live almost anywhere cold. They held it for a long time. The deep cold, the glacial maximum, lasted somewhere in the region of 200,000 years, and while it lasted, the world was cold and shrunken and reasonably stable, and the survivors had time to settle into it and get comfortable. What hadn't happened yet was the melt. Melting an ice sheet is not the reverse of building one. Building takes patience. Snow that survives a summer, then another, piling up until the weight of it turns the pile into something dense enough to creep downhill under its own load. Coming apart is a different physical problem, and it has a habit of accelerating because ice is white and the ground underneath it is not. A white surface throws most of the sunlight that lands on it straight back out. Expose the dark rock beneath, or open a pond of meltwater on the surface, and that patch starts absorbing what it used to reflect, which warms it, which melts more ice, which exposes more dark ground. It is a loop, and it runs in both directions, but it runs faster downhill. So the ice went. The water it had been holding drained back into the ocean. Sea level climbed towards something like where it had started. The shelves reflooded, and the drowned interiors of the continents filled up again. Everything the first phase had taken away was, in the crudest accounting, handed back. And that is when the dying accelerated. The water that came back was not the same water. Start with the simplest piece of chemistry involved, which is that gases dissolve more readily in cold liquid than in warm, the reason a cold drink holds its fizz and a warm one goes flat. Oxygen in seawater obeys the same rule. A cold ocean can physically carry more of it than a warm ocean can, before biology has any say in the matter. Raise the temperature of the ocean by several degrees, and you have lowered the ceiling on how much oxygen it is capable of holding, and nothing alive has done anything yet. Then there is the question of mixing, which matters more. Oxygen only enters the ocean at the top. It arrives out of the atmosphere at the surface and out of photosynthesis in the sunlit layer, and neither of those things is available a kilometre down. The deep sea has oxygen in it only because surface water gets down there. Cold, dense, oxygen-loaded water sinking at high latitudes and creeping along the bottom, which is exactly what it still does today. That circulation runs on density, and density in seawater comes down to temperature and salt. A glaciated world is extremely good at this. The poles are cold, the water there is heavy, it sinks hard, and the whole ocean turns over briskly. Take the ice away and two things go wrong together. The poles warm, so polar surface water is no longer dense enough to sink with any conviction, and an enormous volume of meltwater spreads out across the surface, fresh water, which is lighter than salt water and which sits on top like a lid. The column stops turning over. The layers stop trading. Underneath that lid, the oxygen already present becomes a fixed budget with nothing replacing it, and there is a steady drain on it. Everything living in the sunlit surface eventually dies and sinks, and on the way down and on the bottom, bacteria take it apart. Decomposition consumes oxygen. It is the same reaction as breathing, run by smaller organisms on dead material, and it does not pause because the supply has been cut. So the deep water spends what it has, and then it runs out. Water in that condition has a name, anoxic, from the Greek for without oxygen, and it is the single most important state in this entire story. What happens next is worth slowing down for, because it recurs. Bacteria are far more flexible about respiration than animals are. With no oxygen left, some of them go on pulling energy out of dead material by using a different chemical at the receiving end of the reaction, and one of the most available substitutes in seawater is sulfate. There is a great deal of sulfate in the ocean. After chloride, it is the most abundant dissolved ion there is, so the supply is effectively bottomless. Bacteria running that reaction produce a waste gas, the way we produce carbon dioxide. The waste gas is hydrogen sulfide. It smells of rotten eggs at trace concentrations and kills at concentrations not much above that, and it is lethal to more or less anything with gills or a nervous system. Water carrying it has moved well past being merely short of oxygen. It is actively poisonous. Now hold those two facts against each other. Sea level is rising, the deep ocean is stratified and going sour, and the water climbing back across the drained continental shelves, refilling precisely the habitat that the first phase had emptied, is coming up from below. The sea returned, and it returned wrong. The rock is unambiguous about this. Sediments laid down through that interval in basin after basin worldwide are black shales, dark, organic, rich mudstones, finely laminated, layer on layer with the layering undisturbed. That last detail carries the weight. On a seafloor with oxygen in the water above it, animals live in the mud, burrow through it, and churn the layering into an even paste. Laminations survive only where nothing was down there to disturb them. The graptolites are in those shales as well, pressed flat and preserved as films of carbon, which is what happens when there is no oxygen to rot a soft body and nothing burrowing to break it up. The animals the water killed were preserved by the condition that killed them. The arithmetic is where this event stops behaving the way it is supposed to. In 2025, a group working on Ordovician and Silurian sections dated the whole thing properly. Volcanic ash beds are interleaved with the fossil-bearing rock, and crystals in volcanic ash can be dated with real precision, which means the extinction could be bracketed rather than estimated. Both phases together, start to finish, took about 400,000 years, against the 1 to 2 million that had been the standard figure. And the two phases turned out to be almost nothing alike. The cooling phase occupied 340,000 of those 400,000 years, and species vanished during it at roughly 8% per 100,000 years. The warming phase lasted around 60,000 years, and species vanished during it at 72% per 100,000 years. 8.5 times the rate in under a fifth of the time. This is not the version most people have heard. The end-Ordovician is the Ice Age extinction. It is filed that way in textbooks and museum captions and in nearly every summary written for a general audience, and the framing is not baseless. The glaciation happened. The sea level fall happened. The first phase killed a very large number of things, but the phase that did the bulk of the damage, at a rate the cold never came close to, was the phase in which the ice was going away. The cold was the slow part. It was, in a sense that is uncomfortable to put into words, the survivable part. That is recent work, and one high-precision dating study on a 440 million-year-old event is a thin place to stand. Though it has been through peer review and independent institutional assessment, which is the bar I would want before treating something as the current picture rather than an interesting suggestion. So the first of the 5 scored. By the measure everyone reaches for first, the proportion of things that simply stopped existing, this event is enormous. Something like 80% of marine species, around 40% of genera. Second only to the end-Permian across the whole history of animal life, and second by a comfortable margin over everything else on the list. Measure it another way and it falls off the table. In 2013, a group led by George McGee published a ranking of the major biodiversity crises by ecological severity rather than by body count. Their question was about machinery rather than names, whether the jobs in an ecosystem went on being done afterwards, whether they got done by different kinds of animal, whether any of them stopped being done at all, whether the structure of who eats whom and who builds what came out the other side rearranged. On that ranking, the end-Ordovician comes 6th. Not 6th among all events that have ever happened, 6th on a list that contains the big 5 plus a handful of others, which means it sits below at least one crisis that never made the famous list in the first place. The second largest kill in the history of animals, ranked underneath something most people have never heard of, entirely because of what happened afterwards. What happened afterwards is that the world rebuilt itself into approximately what it had been before. Marine diversity in what is now North America was back to pre-extinction levels within about 5 million years. The reefs returned in the early Silurian, and when paleontologists look at what was constructing them, they find the same families of tabulate corals and the same sponge-like builders that had been doing that work in the Ordovician. Not descendants that had evolved into something else. The same groups, in the same roles, putting up the same kind of structure. Nothing new came out of it either. No body plan turns up afterwards that hadn't existed before, and no group took the opening and became something the world hadn't seen. The survivors filled the space back in with what was already lying around. A specialist in Ordovician seafloors, someone who had spent a working life on them, set down on a shelf, 5 million years after the boundary, and asked what had changed, would have struggled to answer. The water was the right temperature again. The crinoids were standing in their beds, the brachiopods were in the sediment between them, the reefs were going up under the same builders, and the graptolites were drifting overhead. Fewer kinds of everything, in some places noticeably fewer. But the same world, running the same way, doing the same work. 4/5 of the species on Earth had been erased, and the machine was still the machine. So the first entry on the scoreboard has already broken it. On one measure, this event stands second in the entire record. On another, it ranks below crises nobody bothers to name. Both numbers are correct. They describe the same rock in the same ocean over the same 400,000 years, and they disagree because they were never asking the same question. The ranking, on its first attempt, has produced 2 answers and no way to choose between them. Archaeopteris was not quite the first tree-sized plant on Earth. There had been tall things before it, built along stranger lines, trunk-like structures with no real wood in them and almost nothing underground. But Archaeopteris, spreading across the continents through the Late Devonian, something like 375 million years ago, was the first plant that would read to a modern eye, without hesitation, as a tree. Up to about 30 meters tall in the largest specimens. A proper woody trunk, thickening year on year. branches arranged the way branches are arranged now, carrying fronds that were closer to fern leaves than to anything you would see in a garden. It reproduced by spores rather than seeds, so it sits well away from the conifers on the family tree, and yet its wood under a lens looks a great deal like conifer wood. What mattered about it was underneath. Before the Devonian, plants gripped the ground with structures that barely qualified as roots. Shallow anchoring threads, a few centimeters into whatever they were sitting on. Archaeopteris sent roots down on the order of a meter, spread them laterally further than that, and then did it more or less everywhere, because within a few tens of millions of years, these forests had taken most of the habitable land surface on the planet. For the first time, there was soil in the sense we mean the word, not thin mineral grit lying on bedrock, but a deep, worked, organic layer with things living inside it. The rivers changed shape as a result. Water that had spent the previous 4 billion years spreading out across open gravel in braided sheets now ran between banks that held because there were roots in them, and rivers began to meander the way rivers do. Out at sea, the same stretch of time was the best period to be a reef that there has ever been. Reef systems in the Middle and Late Devonian covered something in the region of 5 million square kilometers, a little over half the area of the United States, and roughly 10 times the area of every coral reef alive on Earth today, added together. They were not assembled the way modern reefs are. Corals were part of the structure, but most of the heavy construction was done by sponge-like animals called stromatoporoids, which laid down dense, layered mounds of calcium carbonate, and between them they had built the largest reef province in the history of the planet. The question worth asking is what a root actually does to rock, and the answer is more aggressive than it sounds. Physically, it wedges. A root grows into a crack, thickens, and thickening applies enough pressure to split stone, which is why street trees lift pavement. But the physical part is the smaller part. Roots respire, which pumps carbon dioxide into the soil around them, and carbon dioxide dissolved in soil water makes a weak acid. Roots and the fungi that live with them release organic acids of their own on top of that. So a rooted soil amounts to a bath of mild acid sitting on bedrock, held in place, kept damp, and continuously refreshed for as long as the forest stands. One consequence is the same reaction that may have chilled the Ordovician. Acid working on silicate rock pulls carbon dioxide out of circulation and ends up burying it in the ocean as carbonate. Scale that up from low mats of vegetation to a global forest with roots a meter deep, and you have turned the planet's slowest thermostat up hard. Carbon dioxide fell through the Devonian and temperature came down with it. Carbon was not the only thing coming out of that rock. The element that mattered more has no atmosphere to live in. Phosphorus is essential to everything alive. It is in the backbone of DNA, in the membrane of every cell, and in the molecule that moves usable energy around inside you at this moment. Nothing lives without it. And unlike carbon, and unlike nitrogen, phosphorus has no gas phase worth speaking of. There is none in the air, no reservoir overhead to draw down, no organism that can pull it out of the sky the way nitrogen-fixing bacteria pull nitrogen. Phosphorus comes from rock, and only from rock. It enters the living world by being weathered out of stone, washed downhill, and delivered to the sea. That makes it the throttle on the entire system. How much life the ocean can support is set over long timescales by whichever nutrient runs short first, and nitrogen does not qualify because there are organisms that manufacture usable nitrogen out of thin air whenever the supply tightens. Phosphorus has no such workaround. The productivity of the world ocean across geological time is governed by how fast phosphorus is being ground out of continental rock and carried down by rivers. The Devonian forests ground it out considerably faster than anything had managed before. What happens when phosphorus arrives in shallow water in quantity is not a matter of speculation, because the process is observable at small scale, more or less continuously. If you have ever watched a pond go opaque green in August, you have watched the front end of it. Nutrients arrive, algae bloom, the bloom exhausts its own supply and dies, the dead material sinks, and bacteria take it apart. And decomposition, as always, burns oxygen. The bottom water goes first, then the layer above it. At pond scale, that is a nuisance. At the mouth of the Mississippi, which drains fertilizer off most of a continent, it opens a zone of oxygen-starved seafloor in the Gulf of Mexico every summer that has run past 20,000 square kilometers in the worst years. That is a serious dead zone by any modern standard, and it is a small stain set against the shelf seas the Devonian had to work with. There are two ways to take the oxygen out of an ocean. You can cut the supply, warm the water so it holds less, and shut down the circulation that carries it downward. Or you can raise the demand, deliver so much nutrient that the volume of dead organic material sinking through the water column overwhelms whatever oxygen is there to break it down. The Ordovician did the first, the Devonian did the second, and it did it for a very long time. The idea itself dates to 1998, when Algeo and Scheffler laid out the connection between the spread of rooted plants, the weathering of continental rock, and the black shale intervals in the Devonian marine record. What it lacked for a long while was arithmetic. In 2023, a modelling group supplied some. They scaled up the phosphorus flux coming off Devonian rivers, ran it through a model of the ocean and atmosphere, and got widespread marine oxygen loss out the far end, together with shifts in carbon isotopes, temperature and carbon dioxide that match what the rocks record. Their own conclusion is careful and worth keeping in the shape they gave it. The crisis was multifaceted, with both land plants and volcanism contributing. There was volcanism. A large igneous province in eastern Siberia, the Veluwe Traps, was erupting through roughly the right interval, and nobody working on this is claiming that trees managed it alone. Even so, of the 5, this is the only one where the trigger was alive. Everything else on the list begins with geology, or with something arriving from outside, rock moving, magma rising, an object crossing an orbit at the wrong moment. This one begins with a tree doing what trees do. There is no malfunction anywhere in the sequence. Roots evolved because roots work. Deeper roots reach more water and more nutrient and hold a plant upright in wind, and every increment of depth was rewarded. The forests spread because forests outcompete whatever came before them. Weathering increased because that is what acid does to rock, and the phosphorus went downhill because water goes downhill. And the algae bloomed because algae bloom when they are fed. Then the oxygen went out of the water because bacteria breathe. The land got better at being alive, and the ocean paid for it. What it paid is written in a particular kind of rock. Through the Late Devonian, in section after section, across what was then shallow sea, the Harz Mountains in Germany, quarries in southern Poland, the slate country along the Rhine, the pale limestone gives way twice to bands of black, organic-rich mudstone. They are called the Kellwasser horizons, after a valley in the Harz where they were first described, and they are the same dark, finely laminated, unburrowed material that always marks water with the oxygen gone out of it. The shale tells you the water went bad. It does not tell you where it went bad or how it reached the animals that died, and that has turned out to be a considerably harder question than it looks. The answer, when it came out of North Dakota, and it came in cylinders. Underneath the northern plains, spreading across North Dakota and eastern Montana, and up into Saskatchewan and Manitoba, there is a deep bowl in the crust called the Williston Basin, and low in its fill sits a formation called the Bakken. It is Devonian at the base, running up across the boundary into the Carboniferous, and it is one of the most thoroughly drilled bodies of rock anywhere on Earth because it is full of oil. That last fact is the reason any of this was possible. Decades of drilling left behind a library of physical core, actual cylinders of rock pulled up in sequence, boxed, labelled and shelved. In 2023, a research group worked through 90 of them. A single core tells you what happened at one point on an ancient seafloor. 90, spread across a basin and correlated against one another, tell you something no single core can. Not just what the chemistry was, but where it was and which way it was moving. You stop reading a column and start reading a map that changes with depth, which is to say, a map that changes with time. What the map shows is euxinic water coming inshore. Anoxic water has no oxygen in it. Euxinic water has something in it instead, and the distinction sounds like a technicality until you look at what it does. An animal in anoxic water suffocates, which is slow, and which a certain number of organisms can ride out. Burrowers that shut down and wait, things that tolerate low oxygen for a season until the water turns over. Hydrogen sulfide offers no such option because it does not merely withhold what an animal needs, it attacks the animal directly. It binds to the same site in the respiratory machinery that cyanide binds to, and it disables the cell's ability to use oxygen at all, which means it kills things that still have oxygen available to them. It crosses gill membranes without difficulty. At the concentrations that accumulate in a stagnant basin, it is lethal to essentially anything with a circulatory system, and it is lethal fast. The question that matters for an extinction is not whether sulfide existed down in the deep water. In a stratified ocean, it generally does, somewhere. The question is how high it came. In an ordinary layered sea, there is a boundary at depth where the oxygen gives out and the sulfide begins, and it sits well below the sunlit zone, out of the way of nearly everything that photosynthesizes and most things that swim. Push that boundary upward until it crosses into the light, and the world changes character. The sunlit surface layer, where the food of the entire ocean is manufactured, and where the larvae of almost everything spend their first weeks alive, becomes poisonous. There is a way to prove this happened, and it is a beautiful piece of reasoning. Certain bacteria photosynthesize without producing oxygen, using hydrogen sulfide in place of water as their raw material. They are green and purple, and they require two things absolutely: sunlight and free sulfide. Neither will do on its own. They can live only in the narrow band where the light reaches down far enough to meet the poison. They make distinctive pigments, and fragments of those pigments survive in rock as recognizable molecules hundreds of millions of years afterwards. Finding them in a marine sediment is not circumstantial evidence. It means that when that mud was laid down, in that place, sunlight and hydrogen sulfide were in the same water. There is no other route by which the molecule could be there. The cores show that water arriving on the shelf, not once, repeatedly in steps, advancing landward and upward into shallow water, holding, retreating and coming back. Each advance lines up with a horizon where the fossils thin out or stop altogether. Two of those advances were severe enough to have earned names. The first is the Kellwasser, the pair of black bands in the Harz limestone, at around 372 million years ago. The second is the Hangenberg, at the very end of the Devonian, roughly 359 million years ago, named for another black shale in the same part of Germany. The gap between them is about 13 million years. The entire fossil record of upright walking apes, from the earliest candidate anyone seriously argues for to this morning, covers around 7. And this is the point at which I have to be straightforward about how poorly constrained this whole event is. The end-Ordovician has been pinned down to a resolution of a few 100,000 years. The Late Devonian has not. Published estimates for the total span of the crisis run from about 500,000 years to 25 million, depending on where you start counting and which pulses you decide belong to the same event. That is not a disagreement about detail. It is a 50-fold range on the most basic property an event possesses, which is how long it went on. Whether this is one protracted crisis with a pulsed structure, or several separate crises that happened to share a stretch of stratigraphy and got filed together out of convenience, is genuinely unsettled, and serious people hold both positions. The consequence for any attempt at ranking is immediate. Rate, how much was lost, divided by how long it took, is one of the few measures that can be compared honestly across events. For this one, the denominator is unknown by a factor of 50. What is not in doubt is what the second pulse did to animals with backbones. The Devonian is called the Age of Fishes for good reason, and its dominant group were the placoderms, armoured fish plated across the head and shoulders in bone, some of them modest and some enormous, and successful for well over 60 million years. After the Hangenberg, there are none, not reduced, not clinging on in some refuge. The entire class is absent from the record and never reappears. In 2010, Lauren Sallin and Michael Coates worked through the vertebrate record across that boundary and found that roughly 44% of the higher-level groups of jawed vertebrates disappeared. What survived came through as a very small number of lineages. Ray-finned fishes, which today account for something like half of all vertebrate species alive, passed through as a handful. So did the sharks. So did the tetrapods, the four-limbed animals that had only recently begun walking on land, and every land vertebrate since, every amphibian and reptile and bird and mammal descends from whatever crossed that interval. Afterwards, the record goes quiet. There is a stretch of roughly 15 million years at the start of the Carboniferous, known for decades as Romer's Gap after the paleontologist who first pointed at it, in which four-limbed animals are nearly absent from the rock. Part of that is a genuine shortage of collecting, and new material out of the Scottish borders has filled in a good deal of it over the last decade. But part of it looks like a real absence. The animals that would eventually inherit the land spent 15 million years being rare. And then there is what happened to the reefs, which is the part of this that lasts. The stromatoporoids that had built 5 million square kilometers of tropical reef stopped building, not everywhere in the same season, but across the Frasnian-Furmenian boundary, the construction guild that had run the shallow tropics for more than 100 million years went out of operation. What took over in the early Furmenian were microbial mounds, reefs assembled by mats of bacteria laying down carbonate the way they had in the Precambrian, before any animal existed that could do the work. The ocean did not switch to a different kind of animal reef. It reverted to building reefs without animals in them. Reefs never regained Devonian extent in the rest of the Paleozoic. They did not regain it in the Permian. The systems that eventually matched that scale are Mesozoic, and they are built by stony corals, the group responsible for every reef on Earth today, which did not exist yet and would not appear for well over 100 million years. The reef did not return because nothing capable of building one was alive. The ocean had to wait for a new animal to evolve, which gives us the second entry on the scoreboard, and it disagrees with the first in the opposite direction. On the corrected figures, background extinction stripped out, the arithmetic redone, the Frasnian pulse removed somewhere between 16 and 20% of marine genera. That is the smallest number attached to any of the 5 that can be measured at all. Ranked by body count, this event finishes last. Ranked by how long the damage held, nothing else on the list is close. An entire mode of reef construction went out of service for longer than the span that separates us from the last dinosaurs, and the world had to invent its replacement from scratch. The first of the 5 erased 4/5 of the species alive and altered nothing structural. The The second erased comparatively few and left a hole that required the evolution of a new animal to fill. 2 events, 2 rulers, and the ranking has contradicted itself twice. What follows the Devonian is a long stretch in which the planet is, on the whole, doing well. Forests thicken into swamps productive enough that their remains become most of the world's coal. Amphibians get large. Reptiles appear and push inland, further from standing water than any backboned animal had managed. The continents converge until there is one landmass with one ocean wrapped around it. That takes about 100 million years. And then, in a place that is now Siberia, the crust opens. Why did this one work? Flood basalt provinces are not rare. There have been dozens across the last 500 million years, and a good number of them line up with some disturbance in the record, a warming pulse, an interval of oxygen-poor ocean, a dip in diversity that recovers. Only a handful line up with a mass extinction, and the ones that do are not reliably the biggest. The Columbia River basalts in the Pacific Northwest put out something like 210,000 cubic kilometers of lava, most of it inside about 800,000 years, around 16 million years ago. Individual flows ran hundreds of kilometers from their vents and buried an area the size of a small country. It coincides with a warm stretch of the Miocene. It coincides with no extinction worth the name. Siberia, at the end of the Permian, produced at least 1.7 million cubic kilometers of igneous rock, and possibly 2 or 3 times that. Large, among the largest on the record, but not the largest. The Ontong-Java Plateau in the Pacific outweighs it by an order of magnitude, and did nothing comparable, though most of Ontong-Java erupted under deep water, which changes what reaches the sky. Volume, in other words, is not the discriminating variable. What the magma had to pass through on its way up turns out to be. When people picture a flood basalt, they picture the surface, lava spreading across a landscape in sheets, cooling into the stepped terraces that gave these provinces their name, from the Swedish word for stairs. That part is real, and in Siberia, the stacked flows run kilometers thick in places. But a great deal of the magma never reached the surface at all. Rising magma does not necessarily keep going up. Where it meets a horizontal weakness in layered rock, a bedding plane between one sedimentary unit and the next, it can turn and spread sideways, injecting itself as a flat sheet between the layers, anywhere from a few meters to a few hundred meters thick, and running for tens of kilometers in every direction. A sheet like that is a sill. In Siberia, the sills are extensive enough to make up a substantial fraction of the entire province, and they are stacked, injected at different depths through the same basin, one above another. The basin they were injected into is the point. The Tunguska Basin had been accumulating sediment for a very long time before any magma arrived. Near the bottom, from the Cambrian and Ordovician, there are thick beds of evaporite, salt left behind where shallow seas dried out, along with limestone and dolomite. Higher up sit Permian sediments that include coal, 500 million years of buried carbon in 3 separate chemical forms, in a stack, waiting. Into that stack, the province injected sheets of magma at somewhere around 1100 degrees Celsius. Rock in contact with magma does not simply get warm. Coal at a few hundred degrees begins to break down, driving off its volatile fraction as gas, methane, carbon dioxide, an assortment of lighter hydrocarbons. Limestone heated hard enough decomposes outright, shedding its carbon dioxide and leaving quicklime behind, which is exactly the reaction used to manufacture cement, run underground at continental scale. And organic rich shale cooks the way it cooks in an oil basin, only hotter and faster, converting its carbon to gas rather than liquid. Every sill is wrapped in a zone of rock that has been through this, the contact aureole, and thermal modeling of Siberian aureoles produces a figure worth sitting with. Over the life of an intrusion, a single square meter of aureole generates somewhere between 50 and 80 tons of carbon dioxide. That is a patch of ground you could stand on, delivering the mass of a loaded truck and trailer in gas. Follow that outward. To put 1,000 gigatons of carbon dioxide into the atmosphere, a gigaton being 1 billion tons, you would need an aureole area of somewhere between 12 and 19,000 square kilometers, roughly the size of Connecticut. The area of the Tunguska Basin affected by sills is about 100 times that. This is why the mechanism does not have to strain. Estimates of what the sills could have produced run to something like 100,000 gigatons of carbon dioxide out of the sediment alone, on top of what the magma itself carried up from the mantle, which is put at roughly twice as much again with a very wide uncertainty attached. Meanwhile, the amount of carbon the record actually requires, worked backwards from the isotope shifts through a model of the whole ocean and atmosphere, comes out, converted into the same units at well under half of that combined capacity. The rock could have supplied a good deal more than the evidence demands, which for a proposed mechanism is a comfortable place to be. There is direct physical evidence that the gas did not merely seep out. Where a sill cooked wet, organic sediment, the gas it generated had nowhere to go, and pressure built until the rock above failed. What that leaves behind is a vertical pipe, a chimney of shattered rock punched from the sill straight up to the surface, in some cases more than 1 kilometer across at the top. Hundreds of them have been mapped across the Tunguska Basin. Each one marks a place where the basin vented directly into the sky. One further property of that rock is worth setting down plainly. The Cambrian evaporites at the base of the stack were not simply salt in the table salt sense. Evaporate beds carry chlorine and bromine in quantity, and when halogen-bearing salt is heated in the presence of organic matter, among the products are volatile compounds that take those halogens up with them: methyl chloride, methyl bromide, and their relatives. That is what a large share of the sills were injected into. Rate matters as much as total, and the modelling supplies a figure for that as well, roughly 5 gigatons of carbon a year sustained. The authors are careful about how they frame the comparison, and it is worth taking in the shape they gave it. That rate is likely small set against modern fossil fuel burning. It was also far more protracted enough that the total exceeded the world's known fossil fuel reserves, none of which would have been particularly visible from the surface. If you had stood on the Siberian plain during one of the quiet stretches between eruptive pulses, and there were long, quiet stretches, decades and centuries of them, the view would have been unremarkable. Dark rock underfoot, weathering slowly. Vegetation working its way back into the cracks. Perhaps a haze in the air, perhaps not. The eruptions themselves came and went, and they were episodes. The machinery that actually mattered ran continuously, silently, with no surface expression at all, 1 kilometer and more beneath your boots, through beds of salt and coal that had been lying there undisturbed since the Cambrian. So the answer to why this one worked has remarkably little to do with how much magma there was. There is nothing exceptional about the Siberian magma. It is ordinary flood basalt, chemically unremarkable, erupted in the ordinary way. What was exceptional was the address. The province opened above a basin that had spent 500 million years storing carbon in 3 separate forms with halogen-rich salt buried underneath all of it, and then it drove 2,000 vertical meters of hot rock into the middle of the stack. The same eruption 1,000 kilometers east through Granite Basement is a large and forgettable event. Everything from here is arithmetic. The carbon went into the atmosphere, and the atmosphere is in contact with the ocean across 2/3 of the planet's surface, and it does not stay in the air. Carbon dioxide is unusual among atmospheric gases in that it does not simply dissolve in water, it reacts with it. That single property is why the end-Permian is a more complicated event than a hot planet with a stagnant ocean. The carbon that came out of the Tunguska Basin did three separate things along three separate physical routes, and all three converged on the same animals at the same time. Two of the routes have almost nothing to do with each other. One of them was not in the water at all. The first runs through heat, and its machinery is familiar enough. Carbon dioxide holds warmth in the atmosphere. The atmosphere warms the sea surface, and warm water carries less dissolved oxygen than cold. Warm surface water is also lighter, so it floats on what lies beneath it and stops sinking, and the vertical circulation that delivers oxygen to the deep ocean slows and then halts. Deep water spends the oxygen it already has on decomposition, runs out, and the sulfate-reducing bacteria take over the job and begin manufacturing hydrogen sulfide. The same sequence that ran in the Ordovician, arriving at the same destination from the opposite temperature. What is new here is that the sequence feeds itself. When a seafloor sediment loses its oxygen, its chemistry changes. Phosphorus in ordinary oxygenated mud is largely locked away, bound to iron oxide particles and held out of circulation. Remove the oxygen and those iron compounds dissolve, and the phosphorus they were holding goes back into the water. That matters because phosphorus is the nutrient that sets the ceiling on how much life the ocean can grow. Releasing it stimulates more production at the surface. More production sends more dead material downward. More sinking material means more decomposition, and more decomposition consumes more oxygen, which drives more sediment anoxics, which releases more phosphorus. The loop closes. Anoxia manufactures the conditions for its own expansion, which is why an oxygen crisis in the ocean, once properly underway, no longer requires the original cause in order to continue. The heat did not stop at inconvenient. Oxygen isotopes measured in conodont fossils, the phosphate teeth of a small eel-shaped animal which lock in the temperature of the water they grew in, put tropical sea surface temperatures across the crisis at around 40 degrees Celsius, with figures on tropical land running between 50 and 60. 40 is worth pausing on. It is above the internal temperature of your own body. An ocean at 40 degrees cannot draw heat away from anything living in it, because the gradient runs the wrong way. The water is a bath rather than a coolant. Marine photosynthesis largely shuts down above that mark, and animal metabolic demand climbs with temperature at exactly the moment the water's capacity to supply oxygen is falling, so an animal in hot water needs more oxygen from water that holds less. The fossil record appears to agree with the thermometer. Through the early Triassic, there is a band around the equator where large land vertebrates and many plants are simply missing from the rock. That temperature work rests substantially on one influential study, and I would not want to leave the impression that a number carrying that much weight is settled beyond argument. The second route is the one that usually gets left out, and it is the one that best explains who died. Carbon dioxide is not only a greenhouse gas and not only an acid. Inside an animal, it is a waste product, and disposing of it is a continuous condition of staying alive. Every cell makes it. It diffuses into the blood carries it to a gas exchange surface, lungs on land, gills in water, and it diffuses out into the surrounding medium down a concentration gradient, because there is less of it out there than in here. Raise the concentration out there and the gradient shrinks. When a marine animal cannot shed its carbon dioxide quickly enough, the gas accumulates in its blood and does exactly what it does in seawater. It reacts and the blood turns acidic. Acidified blood carries oxygen poorly because the pigments that pick oxygen up start releasing it too early. So an animal suffering carbon dioxide buildup becomes functionally short of oxygen even in water that has plenty. The condition has a name, hypercapnia, and it kills without any help from suffocation. This is where the argument becomes testable, because animals differ enormously in their tolerance for it. An active swimmer with efficient gills, a strong circulation, and the ability to buffer its own blood chemistry, a fish, a squid, a shark, can compensate for a great deal of dissolved carbon dioxide by ventilating harder and shifting bicarbonate around internally to hold its pH steady. A heavily calcified, slow, poorly ventilated invertebrate cannot. A brachiopod or a crinoid or a rugose coral has no meaningful ventilation, minimal circulation, a low metabolic rate, and very little capacity to regulate its internal chemistry. It also has a large carbonate skeleton to maintain in water that is turning hostile to carbonate. In 2007, Andrew Knoll and colleagues laid out the prediction that follows. The extinction ought to be selective in an unusual way, not by size or by habitat, but by physiology. Animals that could handle carbon dioxide should come through disproportionately, and animals that could not should be devastated. The record matches. The great losers of the end-Permian are the heavily calcified, poorly buffered, largely stationary invertebrates, the corals, the brachiopods, the crinoids, the reef-building foraminifera. The survivors are disproportionately the animals with gills and pumps and adjustable blood chemistry, mollusks, arthropods, fish. Being able to hold your own internal chemistry steady was, at the end of the Permian, the most useful attribute available. The same chemistry went to work on the water itself. Boron isotopes in carbonate rock preserve a record of seawater pH, and they show a rapid, substantial acidification event during the second phase of the crisis, sharp enough that heavily calcified organisms were being stripped out preferentially while it ran. It is a real and well-documented pulse. It is also not the whole account, because it arrives late in the sequence rather than at the beginning. The third route left the ocean entirely. The evaporate beds that those sills cooked through were rich in chlorine and bromine, and heating halogen-bearing salt in the presence of organic matter yields volatile compounds that carry the halogens up with them. Methyl chloride, methyl bromide, and a family of relatives, light, stable enough to survive the ascent, and buoyant. When they reach the stratosphere and ultraviolet light breaks them apart, the halogen atoms released are catalytically destructive to ozone, meaning a single atom destroys a great many ozone molecules and is not used up doing it. Remove enough ozone and the ultraviolet reaching the ground rises sharply. The evidence for this is unusually direct. Plants respond to ultraviolet exposure by loading the outer walls of their pollen grains with compounds that absorb it. A chemical sunscreen built into the reproductive machinery, those compounds survive in rock. Work published in 2023 on latest Permian sediments from Tibet found them spiking hard across the extinction interval, in step with a mercury peak marking the volcanism and with the carbon isotope shift marking the gas. Laboratory work has established what elevated ultraviolet actually does to a conifer, and the answer is not that it kills the tree. It sterilizes it. The pollen comes out malformed and non-viable. The forest stands there, apparently healthy, and quietly stops reproducing. There is one piece of this you have already tested on yourself, without meaning to, every time you have held your breath underwater. What eventually forces you up is not a shortage of oxygen. You have minutes of that in reserve. The urgency that builds, the signal that grows steadily harder to argue with, is your body detecting rising carbon dioxide in your blood and the drop in pH that comes with it. There is a dedicated sensor for it in your brainstem, and it is far more sensitive to carbon dioxide than to oxygen. It is why people who lose consciousness in an oxygen-poor room often report no distress beforehand at all. The alarm is not wired to the thing that is actually killing them. You are carrying, at the base of your skull, a monitor for precisely the condition that ended the Permian, and it is the loudest alarm your body has. Popular accounts of this event tend to stop somewhere around the dead ocean. Volcanoes, carbon, heat, no oxygen, hydrogen sulfide, 90-something% gone. It makes a clean story, and every element in it is real. What the clean version leaves out is that the ocean was under attack by 4 separate mechanisms at the same time: heat, oxygen loss, dissolved carbon dioxide, and ultraviolet from above, and that the field has not settled which of them did the most killing. The most recent serious attempt to weigh them, published in 2024, worked on shallow water communities near the equator and tested the diversity record against several proxies at once. Temperature and nutrient supply explained the pattern of loss better than the alternatives did. The record of where and when oxygen was absent came out looking dynamic rather than steadily anoxic, and the acidification signal came out equivocal, largely for want of enough measurements to test it properly. One study on one setting overturning nothing. But it does suggest that the confident popular ordering, volcanoes, then suffocation, then sulfide, then death, is more confident than the evidence currently supports. 4 mechanisms, every one of them demonstrable, all of them running simultaneously on animals that could defend against some and not others. Nobody can presently say which was decisive. It is entirely possible the question is malformed, and that no single one of them was, that what killed the Permian Ocean was the simultaneity. There is a quarry at Maishan in eastern China where the entire end-Permian extinction is 36 centimeters thick. That is the measured thickness of the interval, from the bottom of the bed, where the marine fossils begin to fail, to the top of the bed, where the Triassic is unambiguously underway. Roughly the length of a forearm. The rock above and below it is limestone, pale and ordinary, deposited on a shallow tropical seafloor over millions of unremarkable years. The crisis interval sits in the middle of that as a set of thin, numbered beds, and the boundary itself, the formal, internationally ratified line between the Permian and the Triassic, the line that divides one era of Earth history from the next, is drawn at the base of bed 27C and defined by the first appearance of a conodont called Hindeodus parvus, an animal whose entire surviving remains are microscopic phosphate teeth. The reason Maishan became the reference section for the whole planet is buried in the middle of those numbered beds. 2 of them, beds 25 and 26, are not limestone at all. They are clay, several centimeters to a few tens of centimeters thick, and the clay is altered volcanic ash, which is the part I find genuinely difficult to put down. The eruptions that killed this ocean also delivered into the sediment that recorded the killing, the material required to time it. Ash contains zircon. Zircon is a crystal of zirconium and silicon and oxygen that forms in cooling magma, and it has 2 properties that make it the most useful object in geochronology. The first is that when it crystallizes, it will accept uranium atoms into its lattice in place of zirconium, but it will not accept lead. Lead simply does not fit. So a newly formed zircon contains uranium and essentially no lead at all. The second is that zircon is close to indestructible. It survives weathering, burial, transport, and a good deal of metamorphism without resetting. Uranium decays into lead at a rate that does not vary with temperature or pressure or anything else. Every atom of lead inside a zircon crystal, therefore, arrived there by decay after the crystal formed, and counting the ratio of the 2 gives the time elapsed. There are 2 separate uranium isotopes decaying into 2 separate lead isotopes at 2 very different rates, which means every crystal contains 2 independent clocks that can be checked against each other. The precision comes from a refinement. Radiation damage inside a crystal can open pathways that let a little lead escape, which makes the sample read young. So the crystals are heated to repair the lattice, then partially dissolved in acid, which preferentially attacks exactly those damaged zones and washes them away. What survives the acid is pristine, and only that is measured. Applied to Meishan, this gives an onset for the marine extinction at 251,941,000 years ago, with an uncertainty of about 37,000 years either way. The boundary itself falls some 39,000 years later, and the whole main extinction interval, the entire collapse of the marine world, took at most 60,000 years. There is a subtlety in those figures worth being honest about. The absolute uncertainties are a few tens of thousands of years, which sounds like it should swamp a 60,000-year event. It does not, because the systematic errors are identical for every sample run in the same laboratory against the same standards, so they cancel when you subtract one age from another. We can say that these two ash beds are 60,000 years apart far more confidently than we can say what year either of them is. The interval is sharper than the date, and the rock carries a warning. About 10,000 years before the fossils start to fail, the carbon isotope record swings sharply negative. A flood of carbon entering the ocean and atmosphere that is depleted in the heavier isotope, which is the signature of carbon that was once organic and buried. The gas arrives first. The dying begins 10 millennia later. 60,000 years for the whole thing. All of written human history, from the first accounts anyone can read to this morning, comes to about 5,000. Run 12 of those end to end, and you have the duration of the worst event in the history of complex life. Which makes what happened on land very strange indeed. The assumption, for most of the time this event has been studied, was that the marine and terrestrial extinctions were the same catastrophe seen from two angles. Recent dating says otherwise. Work published in 2024 on Permian and Triassic sections in southwestern China put high-precision ages on the collapse of the tropical forests and found that it post-dates the onset of the marine extinction by somewhere between 61,000 and 276,000 years, depending on which age model you accept. Worse, the terrestrial collapse does not appear to have happened everywhere at once. It moves with latitude over roughly 1 million years, beginning at high latitudes and progressing through the middle latitudes before finally reaching the tropics. Which makes physical sense once you sit with it. High-latitude ecosystems were tuned to cool, strongly seasonal conditions and had no colder ground to retreat to. Tropical ecosystems were already adapted to heat and had further to go before they crossed their own thresholds, and then they crossed them. The catastrophe was not an event that happened to a planet. It was a front, moving. What drove it on land, if not simply the temperature, may be the variability. A study published in 2024 argues that the extreme warmth of the period supercharged the ocean atmosphere oscillation we know as El Niño, producing swings far larger and far more persistent than anything in the modern record. Continental interiors would have flipped between drought and flood on a cycle of a few years, indefinitely. Plants and land animals can tolerate a hot climate. What they cannot tolerate is a climate that reorganizes itself violently every few seasons because adaptation requires something stable to adapt to. The ocean, with its enormous thermal inertia, damps that kind of variability. The land has nothing to damp it with. That is one line of recent work and not a settled conclusion, but it does account for the asymmetry. The most famous survivor of all this may not be a survivor. Lystrosaurus is the animal in every textbook account of the aftermath. A squat, tusked, barrel-bodied plant-eater about the size of a large dog, so overwhelmingly abundant in the earliest Triassic rocks of South Africa that the interval is named after it. The standard telling has it inheriting an emptied world. The numbers complicate that considerably. Lystrosaurus already made up something like 54% of all specimens at the onset of the crisis, before rising to around 70% afterwards. It was not a species that seized an opening. It was already the most common animal in that landscape, and it became somewhat more so. Then there is the dating. Work published in 2020 argues that the base of the Lystrosaurus zone in the Karoo Basin predates the marine extinction outright, which would mean the most cited terrestrial record of this event is not recording the same interval anyone thought it was. Another 2020 paper takes the argument to its conclusion in its title, calling the disaster taxon status of Lystrosaurus a paleontological myth. So the position is this: we can date the death of the Permian Ocean to within a few tens of thousands of years across a gap of 250 million, and we cannot confidently say whether the most famous land animal of the aftermath was reacting to that event, or to something 100,000 years earlier, or to nothing in particular. The marine clock is extraordinary, the terrestrial clock is still being argued over, and the aftermath did not resolve quickly. Environmental shocks kept returning for another 5 or 6 million years. Groups would begin to recover and then be cut down by the next heat pulse, and a stable, structurally complex ecosystem did not reassemble for 8 or 9 million years after the boundary. On the day the ocean began to fail, nothing was wrong in the tropical forests of what is now South China. The trees were the trees, the insects were the insects. It would stay that way for something on the order of 100,000 years. Far to the south, in the high-latitude forests of what is now South Africa and Australia, the change had already begun and was already well along. There was no moment at which the planet went dark. There were places where it had already happened, places where it was happening, and places where it had not yet arrived, all at the same time for 1 million years. Between the end of the Permian and the next entry on this list, there are 50 million years, which is the longest gap in the whole sequence, and long enough that very little carries across it. The survivors radiate into the space, reptiles get large, and then enormous. The first dinosaurs appear and spend a long time as a minor group. The first mammals appear and are smaller and more minor still. The single landmass finishes assembling and then, very slowly, begins to pull apart. And in the shallow seas along its edges, the chemistry of the water starts to change. The first thing that goes wrong is that the shells get smaller. Not fewer at that stage, and not obviously damaged, just smaller. On the shallow carbonate platforms along the western edge of the Tethys, the sea that separated the northern and southern arms of the supercontinent, and whose sediments are now standing up as limestone in the Austrian Alps, the bivalves and the snails and the small shelled things living in the sediment continue doing what they have been doing for millions of years, and each successive generation does it at slightly reduced size. Then the shells thin. Then, working upward through the rock, they become less abundant, and the variety drops, and the reef framework the whole platform is built on stops being extended. It is worth being clear about what a carbonate platform actually is, because it makes the rest of this legible. On most seafloors, the sediment arrives from somewhere else, rock eroded off a continent, carried down rivers, dropped when the current slows. A carbonate platform is not that. Its sediment is manufactured in place by organisms out of the water itself. Corals, mollusks, calcareous algae and single-celled things too small to see pull calcium and carbonate out of solution and lay it down as skeleton. And when they die, the skeleton becomes the ground. The reef, the sand, the mud, the entire structure down to a depth of kilometers, is accumulated biological product. A carbonate platform is a place where the rock is made of life, and the life is made out of the chemistry of the water. So a change in that chemistry does not merely kill animals. It shuts down the factory that produces the floor they are standing on. The change, when the carbon isotopes are traced, has an unambiguous cause, a very large quantity of carbon dioxide entering the ocean and the atmosphere, with an isotopic signature pointing to a source in the mantle. What that carbon does to seawater is the part that repays slowing down for, because it runs opposite to intuition. Dissolved carbon in seawater exists in three forms that convert back and forth into one another: carbon dioxide itself, bicarbonate, and carbonate. When carbon dioxide dissolves, it reacts with water to make carbonic acid, and the acid immediately gives up a hydrogen ion. That loose hydrogen ion is what makes the water more acidic, and it does not stay loose for long because there is something in seawater that will take it. Carbonate ions take it, and in taking it, they stop being carbonate and become bicarbonate instead. Follow the accounting through. You have added carbon to the ocean. The total quantity of dissolved carbon has gone up, and the concentration of carbonate ions, one specific form of that carbon, has gone down because the hydrogen you added has been converting them into something else. Carbonate ion is precisely what a shell is made from. Calcium plus carbonate is calcium carbonate, and calcium is abundant and never runs short. The limiting ingredient is the carbonate, so an ocean receiving a large slug of carbon dioxide becomes an ocean richer in carbon and poorer in the one chemical form that skeletons are built out of. Normal seawater is supersaturated with respect to calcium carbonate, chemically inclined to precipitate it, which is why building a shell is cheap and why a finished shell does not dissolve. Drop the carbonate concentration and that inclination weakens. At first, the animal simply has to work harder, pumping ions against a less cooperative gradient, spending energy on construction that used to come almost free. Below a certain point, the water becomes undersaturated, and then the animal is spending energy not to build its skeleton, but to stop the skeleton it already has from going back into solution. There is a prediction buried in that, and it is testable. Calcium carbonate comes in two crystal forms, and one of them, aragonite, is more soluble than the other, calcite. Animals that build in aragonite should therefore cross the threshold first. The stony corals build in aragonite, and the stony corals, at the end of the Triassic, were removed from the reefs almost entirely, leaving a gap of several million years in the earliest Jurassic before reef construction resumed anywhere. These were the same corals that had finally, after 100 million years of absence, restored reef building to the world's oceans. They had been doing the job for roughly 40 million years when this arrived. The magnitude of the shift has been measured. Ocean pH fell by at least 0.3 of a unit, which sounds small and is not because the scale is logarithmic. A drop of that size means the concentration of loose hydrogen roughly doubled. As far as anyone has been able to detect, it is the largest acidification event in the entire record of animal life. The carbon came from the Central Atlantic magmatic province, and the most useful way to grasp its size is to look at where the rock is now. There is basalt from this eruption in New Jersey and Connecticut, forming the cliffs along the Hudson. There is basalt from the same eruption in Morocco, in the High Atlas. There is more of it in Portugal and Spain, and more again in Brazil and French Guiana. 4 continents, on both sides of an ocean, all carrying pieces of one magmatic event, because when it erupted, they were a single landmass, and there was no ocean between them. Its original extent is put at around 11 million square kilometers, which makes it the most aerially extensive magmatic event known from the history of this planet, larger than Europe. The erupted and intruded volume is at least 3 million cubic kilometers, and possibly twice that. High-precision dating of the crystals in the lava shows it arriving in 4 distinct pulses spread across about 600,000 years, with the individual pulses possibly lasting no more than a century apiece. And the reason it is called the Central Atlantic Province is that it marks the line along which Pangaea began to tear. The rift that opened underneath those eruptions became, over the following 20 million years, an ocean basin. The Atlantic is the scar. 2 things about all this make me uneasy, and both are worth putting on the record rather than smoothing over. The first concerns the word acidification, which implies a slide, a steady drift downward that organisms might in principle track and adapt to. What the rock shows is pulses. 4 eruptive episodes and a corresponding series of sharp acidification events with partial recovery in between. That distinction matters chemically because the ocean has a defense. Carbonate sediment on the seafloor dissolves to neutralize added acid, and rock weathering on land delivers fresh alkalinity down the rivers. Both work. Neither is fast. They operate on scales of thousands to tens of thousands of years, and a century-long eruption outruns them completely. So, the buffer catches up in the quiet interval, and then the next pulse arrives and outruns it again. What the platforms experienced was not a gradient. It was a sequence of shocks arriving faster than the ocean could absorb them. The second is more awkward. When Stephen Stanley rebuilt the extinction magnitudes and produced corrected figures for the Big Five, he left this one out. Not because it was uninteresting, but because, in his assessment, the timing and the list of marine victims remained too controversial to support the calculation, which produces a genuinely odd position in a story about ranking. Of the 5 events everyone agrees are the largest, there is one whose size nobody is currently willing to state. What is not in doubt is the platform. Working upward through those alpine limestones, the shells get smaller and thinner and rarer, and then the limestone itself gives out, because the animals that had been manufacturing it are no longer there in sufficient numbers to keep the floor accumulating. Lowering the pH of an ocean does not poison anything. It raises the price of being a shelled animal, and then it raises it past what the animal can pay. That accounts for who died. It does not begin to account for who was left, and the reason certain animals walked out of the end of the Triassic and into everything that followed turns out to be almost exactly the opposite of what the usual telling assumes. The usual telling is that the dinosaurs inherited a hothouse. Carbon goes into the air, the world heats up, the competition fails, and the animals that would run this planet for the next 135 million years walk into the vacancy. It is a tidy story, and the evidence has been turning against it for some time. Start with where the dinosaurs actually were before any of this happened. They had been around for roughly 30 million years by the end of the Triassic, having appeared somewhere in the middle of the period, and for most of that stretch they were a minor group. The large-bodied rolls on land, the top predators, the bulk plant-eaters, the armoured things, belonged overwhelmingly to the other branch of the archosaur family, the branch that leads to modern crocodiles. In the late Triassic tropics, that branch was dominant, diverse, and often enormous, and dinosaurs were a marginal presence, uncommon, small, and mostly absent from the largest body sizes. Work on the tropical basin suggests they may have been actively excluded, kept out by a climate that swung too violently between wet and dry for large herbivores to establish. Where they were common was at the poles, which brings us to a lake bed in the Yungar Basin in what is now northwestern China, which at the time was sitting at around 70 degrees north. The sediment there is fine-grained, laminated lake mud, the sort of thing that accumulates in still, deep water where nothing disturbs it. Scattered through it are coarse sand grains and small pebbles, and those have no business being there. Fine mud settles out of quiet water precisely because the water is too quiet to carry anything heavier. A pebble in the middle of a laminated mudstone requires an explanation, and there is really only one available. The lake margin froze in winter, the ice picked up gravel from the shore, and when the ice broke up and rafted out over deep water in the spring, it melted and dropped what it was holding. That is a frozen lake, recorded as unambiguously as a photograph would record it. And in the same sequence, in the same basin, there are dinosaur footprints. So the picture that emerges is close to the reverse of the standard one. Through the late Triassic, dinosaurs are the polar animals, living at high latitude in a place with hard winters and seasonal ice, while the tropics belong to something else. Now consider what a flood basalt actually puts into the sky, because it is not one thing. Eruptions on that scale release carbon dioxide, which is long-lived in the atmosphere and warms the planet over thousands of years. They also release sulfur dioxide, which behaves in an entirely different way. Sulfur injected high enough converts into fine sulfate particles that spread through the stratosphere and reflect incoming sunlight back to space, and the effect is prompt and severe. A sharp drop in surface temperature within months. But sulfate aerosols are heavy enough to settle out, and they do over about 1 to 3 years. Then they are gone, and the carbon dioxide is still there, which produces a specific and rather horrible pattern. Each eruptive pulse throws up sulfur, the sky dims, and the world plunges into a cold snap lasting a few years. The sulfur falls out, the cold lifts, and the world comes out of it warmer than it went in, because the carbon dioxide from that pulse has stayed behind and joined the carbon dioxide from every pulse before it. 4 pulses across 600,000 years, each one a spike of cold laid on top of a rising baseline of heat. An animal in the late Triassic tropics had to survive both. And this is where the physiology decides who is left standing, in a way that is not subtle. A reptile that regulates its temperature from outside has a body temperature that is essentially a fact about the morning, about how much sun there is, how warm the air is, how quickly a rock heats up. An animal that generates and retains its own heat has a body temperature that is a fact about the animal. The second arrangement is expensive. Keeping a body warm from the inside costs something in the order of 5 to 10 times the resting energy of a comparable animal that doesn't bother, which is why a crocodile can go for months between meals, and you cannot go for 3 days without feeling it. Most of what you eat today will leave your body as heat. In a stable, warm world, not paying that cost is a straightforward advantage. You need a fraction of the food to occupy the same territory. The moment the sky dims for 3 years, the arithmetic inverts completely, and it inverts fastest for large animals in places that have never been cold because they have no behavioral repertoire for it. No burrows, no dormancy, no insulation, no evolved response of any kind to a season that has never happened. The direct evidence for insulation in Triassic dinosaurs is thinner than one would like, and worth being honest about. Nobody has recovered a feathered dinosaur from those polar lake beds. What exists is an inference from the shape of the family tree. Filamentous body coverings are known from pterosaurs on one side and from bird-hipped dinosaurs on the other, which brackets the group and implies that some kind of insulating fuzz was present in their common ancestor rather than invented later. That is a reasonable inference, and it is not a fossil. What is not an inference is the outcome. Across the boundary, the crocodile-line archosaurs, the large land predators, the armored plant-eaters, the whole dominant assemblage of the late Triassic tropics, are almost entirely removed. What survives from that branch is a handful of small, mostly semi-aquatic forms that eventually become crocodiles. And the dinosaurs, previously a polar curiosity, spread into every latitude and every body size available and stay there. The conodonts do not. The eel-shaped animals whose microscopic phosphate teeth appear in Cambrian rock, whose species defines the base of the Triassic, which crossed the draining of the Ordovician shelves and the poisoned Devonian shallows and the 60,000 years that emptied the Permian Ocean, 300 million years of continuous presence in the record, end here. The last of them are in latest Triassic rock, and there are none above it. In the tropical interior of that continent, when the first pulse went up, you would have noticed. Not the eruption itself, which was thousands of kilometers away, but the sky over the following months. A haze that did not clear, a sun that could be looked at directly, sunsets in colors that had no business being there. And then a cold that arrived and did not lift the following spring, or the one after. Frost in a place that had never had frost, on plants with no mechanism for surviving it, among animals that had never in the history of their lineage needed to be warm without the sun's help. It would have felt at the time like weather. The animals that took this planet and held it for the next 135 million years did not get it because the world grew warm. They got it because 4 times in 600,000 years, the sky went dark and the temperature dropped, and they were the only large animals on the continent already built for that. It was morning on a shallow tropical coastline 66 million years ago. The place is now the Yucatan Peninsula, and at the time it was the edge of a warm carbonate platform, the same kind of arrangement that had been building limestone out of seawater for most of the preceding 200 million years. Rudest bivalves in dense thickets, ammonites in the water column, mosasaurs, which were large marine lizards and very good at their job. Inland, dinosaurs in a landscape of flowering plants and conifers that would be broadly recognizable to a modern eye, with small mammals in it, mostly nocturnal, mostly the size of a rat or smaller. One detail about the ground matters more than any of the biology. Beneath the limestone of that platform, running down for several kilometers, lay thick beds of calcium sulfate, evaporate, laid down when the sea had repeatedly dried out across the shelf. Limestone over sulfate rock, kilometers of it, sitting in exactly the wrong place. Looking at the right part of the sky that morning would have bought you a few seconds of warning, not more. The object was dark. It was moving at roughly 20 kilometers a second, and it did not become bright until it was inside the atmosphere, which it crossed in something under 5 seconds. For an object that size, the atmosphere is barely there. It does not slow it, does not break it up, does not deflect it. It simply gets pushed aside, and the air in front is compressed hard enough to glow. The object was around 10 kilometers across, an asteroid rather than a comet on the current evidence, and it arrived at a steep angle, around 60 degrees from horizontal, which is close to the worst possible geometry, because a steep impact drives the maximum amount of energy straight down into the target and vaporizes the maximum amount of it. The energy released is estimated at somewhere between 7 times 10 to the 23rd joules and 3.4 times 10 to the 24th. That number is difficult to hold, so here is a way to hold it. The sun delivers energy to the entire Earth, the whole daylit hemisphere continuously, at a known rate. The impact released somewhere between about 6 weeks and 7 months of that total planetary sunlight budget. All of it in a few seconds, all of it into a single point. At contact, the shock pressure ran to hundreds of gigapascals, which is well past the point where rock behaves like a solid. The projectile and a comparable mass of the seafloor beneath it were vaporized outright, and the temperature in the first moments exceeded 10,000 degrees, roughly twice the temperature of the surface of the sun. That condition lasted minutes at most, and it was confined to the immediate site, and it is the least consequential thing in this account. What followed was excavation. A transient cavity opened on the order of 100 kilometers across and 30 kilometers deep, and the rock that had been occupying that volume left, some of it at above escape velocity, gone from the planet entirely, most of it thrown onto ballistic arcs that carried it clear of the atmosphere. A hole of those proportions is not stable. Within minutes, it collapsed. The floor rebounded upward, overshot, and fell outward into a ring of shattered peaks around the center, which is why, when a drilling expedition went out into the Gulf of Mexico in 2016 and cored straight down through that ring, what came up was granite. Basement rock that had been sitting 10 kilometers underground was standing above the seafloor inside of a few minutes, and above it the cores record something like 130 meters of material deposited over the course of roughly a single day. The global part of the event was the material that went up. Ejecta thrown clear of the atmosphere follows ballistic trajectories, which means it comes back, everywhere, within about an hour, distributed across the whole planet by the geometry of the arcs. And every fragment re-entering the atmosphere does what any object re-entering the atmosphere does. It heats by compression and glows. Multiply that by the mass of a small mountain range arriving simultaneously worldwide, and the upper atmosphere becomes an emitter. Models put the resulting thermal radiation at ground level somewhere between 5 and 15 kilowatts per square meter, which is a figure with a familiar analogue. It is the output of a domestic oven's broiler element. At the distance, you would hold something under it. For about an hour, the entire sky did that. That said, the popular version of what followed, a single global firestorm, is more uniform than the evidence supports. The thermal pulse was strongly directional, following the trajectory of the impactor. Downrange, it was more than sufficient to ignite vegetation thousands of kilometers away. Uprange, at most sites, it fell short of igniting even the most flammable material available. There is also a live argument, unresolved, about whether the earliest arriving ejecta partially shielded the ground from the radiation of everything that came after it, which would reduce the totals considerably. Fires certainly burned, most of them starting within the first day, with debris still coming down for 2 or 3 days after that. They were not evenly distributed, and they were not everywhere. The ground moved on a scale no tectonic earthquake can approach, and the water responded the way water responds to a hole being punched in the seafloor. Waves that stood 50 to 150 meters high around the margins of the Gulf, running more than 100 kilometers inland in places, and then draining back out and dragging a continent's worth of loose material with them into deep water, where it settled into beds that can still be read. What is worth noticing about all of this is how little of it is mysterious. Every other event in this sequence required a chain of arguments about weathering rates, about ocean circulation, about which of 4 simultaneous chemical insults did the most damage, about whether the land died at the same time as the sea. This one is mass, velocity, angle, and what the ground happened to be made of. Everything in the first hour follows from those 4 numbers by ordinary mechanics. Kinetic energy becomes heat. Heat vaporizes rock. Displaced rock goes up. What goes up comes down and heats the air on the way. Water fills a hole. There is no step in it that requires anything unusual to be true about the Earth, or about chemistry, or about life. By the following morning, it is, in the physical sense, finished. The debris has stopped falling. The waves have run themselves out. The fires are burning down toward whatever they will leave behind, and the ground has gone still, and essentially nothing that mattered has happened yet. None of the killing that matters was done by force. The blast, the fires, the waves and the ground motion were all real, and within a few thousand kilometers of the Gulf, they were comprehensive. They also cannot account for a global extinction because most of the planet was not within a few thousand kilometers of the Gulf. Something reached everywhere, and what reached everywhere was a change in the light. An enormous quantity of pulverized rock went into the upper atmosphere, along with sulfur from the evaporate beds and soot from whatever burned. Coarse material falls out quickly. The heavier a particle, the faster gravity retrieves it. Fine material does not. Below a certain size, a particle suspended above the weather has no efficient way of coming down because there is no rain up there to wash it out, and its settling velocity is measured in meters per day. It circulates, it spreads, and while it is up there, it does the one thing that matters, which is to intercept sunlight before it arrives. Photosynthesis has a threshold. Below a certain level of illumination, a plant or an alga stops fixing more carbon than it burns, and from that point it is running at a loss. Land plants can absorb that for a while. A tree has reserves, a root system and stored sugar. The ocean cannot. Marine phytoplankton are single cells with generation times measured in days and no reserves worth the name, and they constitute the entire base of the marine food web. When the light goes below threshold, the surface ocean stops producing food within weeks, and everything above it in the chain begins to fail immediately afterwards, from the bottom upward. For about 40 years, the accepted agent of that darkness was sulfur. Vaporized calcium sulfate from the target rock converts to sulfate aerosol in the stratosphere, reflects sunlight and cools the surface hard, the same process that produces cooling after large volcanic eruptions scaled up beyond anything volcanic. That was the textbook mechanism, and it has been substantially rewritten twice in the last few years. In 2023, a group working on an unusually thick and well-preserved boundary deposit in North Dakota did something straightforward. They measured the grain sizes in the ejecta layer. What they found was a far larger fraction of very fine silicate dust than anyone had assumed. Particles under 1/100th of a millimeter across, small enough to remain aloft for a very long time. Feeding the measured size distribution into a climate model gave an atmospheric residence time for that dust of roughly 15 years, and a winter driven principally by rock powder rather than by sulfur. Then, in a paper published in 2025, a second group approached the sulfur question empirically, instead of by calculation. Rather than modelling how much sulfur ought to have been released given the target volume, they measured sulfur concentrations and isotope ratios in the impact structure itself and in boundary ejecta from a set of terrestrial sites and worked back to the quantity released. The figure they arrived at is 67 billion tonnes, plus or minus about 40, roughly 5 times lower than the numbers the standard model had been using. So within 2 years, the leading actor changed. Sulfur came down by a factor of 5, and fine dust came up, and the shape of the winter changed with them towards something that began less violently and lasted a great deal longer. 15 years is the time the dust needed to finish falling out, and the deepest darkness occupied the early part of that rather than all of it. Even so, a child born in the week of the impact would have been an adult before the atmosphere was properly clear again. Now work forward from the physics, because the sorting that follows falls out of it with very little slack. If sunlight stops arriving in useful quantity, the question facing every organism on the planet reduces to a single one. Where do your calories come from, and how recently were they made? Anything eating live plants is in immediate trouble, and anything eating the animals that eat live plants is in trouble one step behind. On land, essentially every terrestrial vertebrate above about 25 kilograms disappeared, and the reason is not that large animals are fragile. It is that a large animal requires a large and continuous supply of food, and the supply had stopped being produced. But not all food is made this week. A forest floor is a bank of stored carbon, leaf litter, dead wood, fungal networks, soil organic matter, representing years of accumulated photosynthesis that has already happened. Decomposers run on that, and so does everything that eats decomposers. Insects, worms, fungi, and the small animals feeding on them were drawing on a reserve rather than on current production, and the reserve did not care about the sky. Freshwater systems ran on the same principle at larger scale. A river ecosystem is substantially fueled by material washing in from the land, leaves, wood, organic debris, rather than by algae growing in the water. That is why freshwater vertebrates came through at rates that look almost anomalous against the terrestrial record. Turtles, crocodilians, amphibians and freshwater fish survived in numbers, in the same landscapes where the dinosaurs did not, because their food supply had a delay built into it. Dormancy did the same work in the open ocean, and did it with a precision that is almost experimental. Among the plankton, dinoflagellates, single-celled organisms that can form tough resting cysts and settle out to wait, survived the boundary comparatively well. The plankton that could not form resting stages, including the chalk-forming algae and the shelled, single-celled organisms of the surface layer, were removed at rates approaching total. Same water, same event, same duration of darkness, and the deciding variable is whether the organism had an off switch. Plants use the same trick above the waterline. A seed is stored photosynthesis wrapped in a delay mechanism, and a root system is a plant with the option of starting over. Immediately above the boundary in section after section, the pollen record is overwhelmed by fern spores, the fern spike, because ferns reproduce by spores, colonize bare disturbed ground faster than anything else, and were the first thing to reoccupy landscapes that had been stripped. The cleanest demonstration of the whole principle sits in the deep sea, and it is worth stating carefully because it looks like a contradiction. At the KPG boundary, the plankton living in the sunlit surface layer suffered one of the most severe extinctions in the marine record, the great majority of species gone. On the seafloor, directly beneath them, the shelled single-celled organisms living in the mud experienced comparatively minor extinction. Their communities were dramatically reorganized, the species proportions rearranged, but the wholesale loss simply is not there. They are in the same ocean, in the same water column, separated only by depth. What separates them is that the surface organisms were eating photosynthesis as it happened, and the seafloor organisms were eating what fell, a slow rain of dead material from above, already delayed by weeks or months in transit, in an environment where food arrives unpredictably and starvation is a normal operating condition. They were already built for a bad year. The bad year came, and it was longer than usual, and a great many of them were still there afterwards. So what the filter was actually sorting on was not body size, which is only a proxy. It was distance from live photosynthesis. Everything that could eat the dead, or wait inside a seed or a cyst, or live off carbon that had been fixed years earlier, came through in numbers. Everything that needed the sunlight of that particular morning, or ate something that did not. You are here because of that rule. The mammals alive at the boundary were, on the current reconstructions, small, probably nocturnal, probably capable of getting underground or under cover and eating insects. Not a promising set of attributes in a world run by animals that had held it for 135 million years. Every one of them turned out to be the right thing to have, all of which rests on the assumption that we know what caused it. That assumption is younger than it looks. It began with a measurement taken to answer an entirely different question, and it has been under sustained pressure for most of the time it has existed. In the early 1970s, a geologist named Walter Alvarez was spending a good deal of time in a gorge outside the town of Gubbio in central Italy, looking at limestone. The rock there is pink, fine-grained, and beautifully continuous. It accumulated on a deep seafloor over tens of millions of years without interruption, which makes it useful for calibrating other things. Running through it, at the Cretaceous boundary, is a layer of clay about a centimetre thick. Below the clay, the limestone is full of the shells of surface-dwelling plankton. Above it, they are almost entirely absent. The question Alvarez wanted answered was not what killed them. It was how long the clay had taken to accumulate, because that number would tell you how long the extinction had lasted and whether it was a catastrophe or a decline. His father, Luis Alvarez, was a physicist, and he suggested a way to turn the clay into a clock. Cosmic dust falls onto this planet continuously and at a reasonably steady rate, and it carries elements that are almost absent from the Earth's own crust, iridium among them, because when the Earth differentiated, iridium went down with the iron into the core. So the amount of iridium in a sedimentary layer is a rough measure of how long that layer spent lying at the surface collecting dust. A lot of iridium means slow deposition. Very little means fast. The samples went to Frank Asaro and Helen Meischel, two nuclear chemists at Berkeley who had developed the technique required to measure trace elements at those concentrations, irradiating the sample in a reactor and reading the radiation given off by the products, which allows quantities far too small for ordinary chemistry to be counted. The clock came back broken. The iridium in the clay was far above anything the surrounding limestone contained, and far above anything a centimetre of slowly accumulating sediment could possibly have collected. Read at face value, the stopwatch said the layer had taken millions of years to form, which everything else about the section flatly contradicted. So either the assumption about steady cosmic dust was wrong, or the iridium had not arrived gradually at all. It had arrived all at once, from a single object large enough to carry that much of it. The paper came out in Science on the 6th of June, 1980, under 4 names, and it did propose the impact. It was not a cautious note about an unexplained anomaly, whatever gets said about it now. What it did not have was a crater. That gap lasted 11 years, and the strange part is that the crater had, in a sense, already been found. In the late 1970s, 2 geophysicists working for the Mexican State Oil Company, Glenn Penfield and Antonio Camargo, had mapped a large circular anomaly in gravity and magnetic data beneath the Yucatan and recognized it as a probable impact structure. They said so publicly in 1981. Almost nobody working on the extinction noticed, and almost nobody working on the extinction was reading Petroleum Geophysics Conference abstracts. The hypothesis and its physical evidence sat in separate rooms for a decade before anyone put them together in 1991. None of which is the hard part. The hard part is in west-central India, where roughly 500,000 cubic kilometers of basalt sit in stacked flows over an area the size of a large country. The Deccan Traps were erupting across the Cretaceous boundary, before it and after it, and by any reasonable standard, they are one of the largest volcanic events in the history of the planet. Everything established about what a flood basalt on that scale does to a climate applies here, so there are 2 candidate causes, both enormous, both real, and both in the right place in the rock. The question is the order. In February 2019, 2 teams published in the same issue of the same journal, using different dating techniques on the same lava sequence, and reached conclusions that cannot both be true. One team, led by Blair Schoener, dated zircon crystals from ash layers within the flow sequence using uranium and lead. They found the eruption arriving in 4 discrete high-volume pulses separated by quiet intervals, with one pulse falling between 300 and 150,000 years before the boundary, and the largest of them centered on the final 100,000 years of the Cretaceous. On that reading, a very large volcanic event was well underway before the asteroid arrived and could have done substantial damage on its own. The other team, led by Courtney Sprain, dated the lavas directly, using the decay of potassium into argon measured through argon isotopes. They found roughly 3/4 of the total volume erupting after the boundary. On that reading, the volcanism arrives too late to have caused anything, and the impact stands alone, with the further suggestion that the impact itself may have shaken the eruption into its highest gear. Both teams are careful. Both results have survived scrutiny, and the reason they disagree is worth understanding because it is a limit rather than a mistake. The uranium-lead method dates the crystals in the ash beds, which are the material that settled during the pauses between eruptions. It is exquisitely precise about those crystals, and translating that precision onto the lavas themselves requires assumptions about how the pauses map onto the flows. The argon method dates the lava directly, which is the thing you actually want dated, but it carries larger uncertainties and depends on calibration against standards. On top of that, the two techniques have a small known systematic offset relative to one another, a fraction of a percent. And a fraction of a percent at 66 million years is somewhere around 60,000 years, which is precisely the size of the interval being argued about. Here is the comparison that makes the whole problem visible. The impact took a few seconds. The Deccan eruptions took roughly 750,000 years, and the best dating available to anyone can resolve these events against each other to something like 100,000 years. Asking which came first is asking a question about a moment using instruments that measure in millennia. What both camps agree on is that the impact fell within about 50,000 years of the eruption's peak. Two of the largest events in the history of this planet, arriving effectively simultaneously, and 45 years of concentrated work has not been able to pull them apart. There is a third position, seriously argued, that the two are not rivals at all, that the seismic energy released by the impact propagated through the planet and destabilized a magma system already primed on the far side of it, in which case the volcanism is a consequence of the impact rather than a competitor to it. There is a second question in the same condition, and it is the one most people think is settled. Were the dinosaurs already in decline? In 2019 and 2020, two separate groups argued that they were not, that the apparent thinning of dinosaur diversity through the last few million years of the Cretaceous is an artifact of the rock, not of the animals. Sea level was falling, the environments that preserve fossils were shrinking, and if there is less rock of the right kind from the right interval, you will find fewer species in it, regardless of how many were alive. In 2021, two other groups argued the opposite, using statistical models of speciation and extinction rates, and found a genuine decline beginning some 10 million years before the impact. A review published in 2023 worked through the modelling and concluded that the models do not settle it either way. Every party to that argument is competent. The disagreement is not about carelessness. It is about what the fossil record is physically capable of telling you when the thing being measured and the thing distorting the measurement change at the same time. So it is worth being exact about what you are entitled to believe. The impact happened, that is not in question. It was enormous, it is dated to the boundary, and the ejecta layer is on every continent. What is not established is whether the volcanism contributed materially to the extinction or arrived too late to matter, and whether the animals it killed were already on their way down. Both of those remain open on the most studied extinction in the history of the science, with the best rock, the best dating, and 4.5 decades of concentrated effort behind them. Causes are the hardest thing in geology to establish, because a cause has to be dated against its effect, and the dating is never quite good enough. Effects are easier. Effects you can simply count. There is one measurement every event on this list can be made to give up without any argument about triggers or mechanisms or which of 4 simultaneous insults did the most damage. However it happened, and whatever it was, the world afterwards took a certain amount of time to put itself back together. That number can be read off the rock, and it does not care about causes. Here they are, in the order the events happened. The end-Ordovician, about 5 million years, after which the shelves were occupied at roughly the same density by the same categories of animal, doing the same jobs in the same arrangement. The Late Devonian, 10 to 20 million years before 4-limbed animals reappear in the record in useful numbers, and somewhere north of 100 million before reef construction returned to the scale it had operated at before, because the work had no qualified applicant until an entirely new group of corals evolved to take it on. The end-Permian, 8 to 9 million years before a structurally complex ecosystem held together, and through the first 5 or 6 of those, partial recoveries kept assembling and then being taken apart again by the next pulse of heat, over and over, before anything managed to stick. The end-Triassic. A few million years, which is the shortest figure on the list and also the least reliable, and those two facts are related. The event whose magnitude nobody will state is not going to have a well-constrained recovery either. The end-Cretaceous. At the crater itself, the ocean's production of organic matter was running abnormally for about 1.2 million years, and severely so through the first 320,000. Set out like that, the numbers look straightforward. They are not, because the word doing the work in all 5 of them is doing more than one job. Consider what happened in the ocean after the impact. Work published in 2019 found that the biological carbon pump, the process by which organic matter produced at the surface is transported into the deep sea, which is the single most consequential thing the ocean does chemically, came back to something like normal operation on a much shorter timescale than diversity did. The ocean was working again long before it was full again. Species counts were still deeply depressed, while the machinery those species collectively run was already turning over at close to its old rate. Which forces a distinction that the phrase recovery time quietly hides. An ecosystem can be functional and impoverished at the same time. Fewer species were doing the job, and they were doing it. So the question, how long did recovery take, has at least 2 answers depending on whether you mean the return of the function or the return of the variety, and they can differ by millions of years. There was also no single global curve to speak of. Looking at the earliest Paleocene ocean, sites in the Gulf of Mexico, the North Atlantic, and the Old Tethys record a drop in productivity, while sites in the Central Pacific over the same interval record a rise. Same planet, same aftermath, opposite signs. Whatever the ocean recovered means, it did not mean the same thing everywhere at once. What the aftermaths do share is a look. After the Ordovician shelves refilled, a single cold water assemblage of brachiopods occupied continental shelves worldwide. The same handful of species everywhere for a geologically brief period. After the Devonian reef builders stopped building, the mounds that took their place were constructed by bacterial mats, an arrangement the ocean had abandoned before animals existed and returned to for lack of an alternative. In the earliest Triassic beds of southern Africa, one squat tusked plant eater accounts for something like 7 specimens in every 10, though whether that reflects the crisis or a trend already well underway is contested. And in the ocean immediately after the impact, the plankton assemblages are dominated by 2 or 3 species present in quantities no functioning ocean would normally support, while on land, the pollen record for a stretch consists almost entirely of fern spores. A broken world does not look empty. It looks the same everywhere you go. Abundance is often perfectly good. There can be enormous quantities of biological material moving around, but it is all the same material, and it is doing all the same things, and you can travel a very long way without encountering anything you have not already seen. There is something in those recovery numbers worth staying with, and it is not their size. A recovery interval is not an event. Nothing experiences one. Take the shortest of the 5 million years. An animal with a generation time of a year lives and dies 5 million times inside that interval, which is several hundred times the total number of generations our own species has produced since it appeared, and not one of those 5 million generations is in a position to know it is living in an aftermath. Each is born into whatever the world happens to be at that moment, finds it entirely ordinary, and hands it on very slightly altered. The corridor is real. Every lineage that crossed one of these intervals crossed it that way. One generation at a time, with no reference point, no way of registering that the number of things it was competing with was a fraction of what had been there, and no sense whatever of direction. The recovery is only visible from outside and from a distance, and long afterwards. What crossed, in every case, was something small and unspectacular that happened to still be present when the counting resumed. Every one of those corridors is in your ancestry, and not in a figurative sense. It is a chain of individual organisms, each of which was alive and managed to reproduce, running without a single break from before the Ordovician shelves drained to whatever room you are lying in now, through the sulfidic shallows and the collapse of the reef builders, through the 15 million years when four-limbed animals were rare enough to leave almost no trace, through the early Triassic heat pulses that kept resetting the recovery, through the years without a clear sky. Not one of your ancestors at any point across 440 million years failed to reproduce. The chain has never once been interrupted, or you would not be at the end of it. So recovery gives a fourth way of ordering these 5 events, and it agrees with none of the ones already on the table. Not with the ranking by how many things died, or by how fast they died, or by how much of the world's working structure came apart. At some point, that stops being an inconvenience and starts being the finding. You were promised a ranking. There are 5 of them. They were all built by competent people using defensible methods on the same body of evidence, and no 2 of them produce the same order. What follows is what happens when you lay them side by side. Start with the measure everybody reaches for first, which is how much of the living world stopped existing. When Stephen Stanley rebuilt those figures, subtracting out the ordinary background rate of extinction that continues right through any crisis, and correcting for the way the fossil record smears a sudden loss backwards in time, the numbers came out considerably smaller than the ones in circulation. At the level of genera, the end-Permian removed about 62%, the end-Ordovician 42 to 43, the end-Cretaceous 38 to 40, the Frasnian pulse of the Late Devonian somewhere between 16 and 20%, which is the smallest number attached to any of them. And the end-Triassic he left out entirely, on the grounds that the timing and the list of casualties were too unsettled to support the arithmetic. Now put those against the definition. A mass extinction, in the sense the term is normally used, means the loss of more than 75% of species within a geologically brief interval. Translated to species level, only the end-Permian, at around 81%, clearly clears that line. 4 of the big 5 do not meet the definition of a mass extinction. That is not a rhetorical flourish. It is the direct consequence of correcting the arithmetic, and it is why the founding category has been coming apart for 40 years while the phrase has stayed exactly where it was. But magnitude on its own is obviously insufficient because it has no denominator. Losing 40% of everything over 20 million years is a different physical event from losing 40% over a single afternoon, and the fossil record does not distinguish between them unless somebody insists on it. So, rate. Here the order rearranges immediately. The end-Cretaceous goes to the top because the trigger took seconds and the mechanism that did the killing was fully underway within weeks, although the honest version is that the rock cannot resolve it that finely, and what we can actually say is that the event was faster than the resolution of the instrument. The end-Permian is second, with its main interval compressed into at most 60,000 years. The end-Ordovician is close behind on duration, with a lethal pulse of around 60,000 years, though it killed considerably less inside that window. The end-Triassic comes fourth, distributed across 4 eruptive pulses over roughly 600,000 years. And the Late Devonian cannot be placed at all because its duration is published anywhere between 500,000 years and 25 million. An event whose length is uncertain by a factor of 50 cannot be ranked by speed. It simply drops off the sheet. Neither of those measures asks the question that most people actually mean when they ask which was worst, which is not how many names disappeared, but how much of the world stopped working. In 2013, a group led by George McGee ranked the major crises on exactly that basis. Whether the jobs in an ecosystem continued to be done, whether they were taken over by different kinds of animal, whether any of them stopped being done at all. The end-Permian holds first place, as it does on every other measure. Second place goes to the end-Cretaceous, which is the least taxonomically severe of the five and the second most ecologically severe event of the entire last half-billion years. The Devonian crises occupy the middle, and the end-Ordovician comes sixth. Not sixth of five, obviously. Sixth on a list that includes the Big Five plus several others, which means it sits below the Serpukovian crisis in the middle of the Carboniferous, an event that has never appeared on anybody's list of anything. The second largest kill in the history of animal life, ranked underneath a crisis most working paleontologists would have to look up. Because when the Ordovician survivors rebuilt, they rebuilt the same world. Recovery gives a fourth ordering, and it has its own defect, which is that it is not measured the same way twice. Reckoned by how long a structurally complex ecosystem took to hold together, the end-Permian is longest at 8 or 9 million years. Reckoned by how long a particular group stayed suppressed, the Late Devonian is longer, with four-limbed animals scarce for 10 to 20 million years and reef construction absent at scale for more than 100. The end-Cretaceous is the fastest, at something like 1 to 2 million. But comparing those figures against each other means comparing an ecosystem-level measure with a group-level one, and the answer changes depending on which you pick. Then there is the fifth ruler, and it is the one that changes the picture most. Ask not how much was lost, but how much never came back, and the Late Devonian goes to the top by a wide margin. An entire mode of reef construction went out of service and stayed out for well over 100 million years, and it only returned because a different group of corals evolved from scratch and took the job on. Second is the end-Permian, after which the seafloor was permanently reorganized. The brachiopods and crinoids that had dominated shallow marine life for 250 million years never recovered their position, and the mollusks that replaced them are still holding it. Third, the end-Cretaceous, which removed one particular group of large land animals and handed the vacancy to a set of small nocturnal ones. Fourth, the end-Triassic, which ended a class of chordates that had run continuously for roughly 300 million years. And fifth, at the bottom, the end-Ordovician, which killed more species than any of them except the Permian, and changed nothing structural whatsoever. So here is the tally. The end-Permian takes first place on 3 of the 5 measures. Not all 5, which is worth noticing, because the assumption that it wins outright is so widespread that the exceptions rarely get stated. It loses on rate to the end-Cretaceous, and it loses on permanence to the Late Devonian. The end-Ordovician takes second place on the ranking everybody quotes and finishes last or near last on 3 of the other 4. The end-Triassic cannot be scored at all on magnitude because nobody will state a figure. At which point the sensible thing is to stop asking which was worst and ask what the question was doing. Every one of those 5 rulers has a value judgment welded into it. Counting species treats variety as the thing worth having. Counting rate treats suddenness as an aggravating factor, though it is not obvious why an event should be worse for being fast if the total is identical. Counting ecological severity treats the machinery as more important than the inventory. Counting recovery treats a return to something like the previous condition as the standard. Counting permanence treats irreversibility as the real damage. Those are 5 different opinions about what a world is for, expressed as measurements, which is why they disagree. They were never measuring the same property, and the disagreement is not noise or imprecision. It is information. It says that these 5 events have far less in common than the collective name implies, and that lumping them together is a decision about vocabulary rather than a discovery about the planet. There is one more thing worth putting on the record, and it lands squarely on the least measurable of the 5. In the 1982 analysis that produced the Big Five in the first place, working at the level of families, the end-Triassic came out as the mildest of them, least intense, the runt of the set. Later work, correcting for the incompleteness of the record and detrending the long-term decline in extinction rates that runs through the whole Phanerozoic, has moved it substantially, far enough that it now appears among the 3 largest extinction events of the last 500 million years. The event that the founding paper ranked last is not last. It may be third. Nobody can currently say by how much, because it is also the one event on the list whose magnitude no one is willing to estimate. 5 rulers, 5 orders, and 1 event that changes position depending on which decade you ask. All of which can be done, and has been done, and is the ordinary business of the field. But every one of those measurements shares a single requirement, without which not one of them can be calculated. The event has to be finished. Everything in this account happened inside the most recent 1/10 of this planet's existence. The Earth is about 4.5 billion years old. The oldest of the 5 events sits at 443 million, which places all of them comfortably in the last stretch, the interval during which animals had hard parts, and hard parts fossilize, and fossils can be counted. Before that, there are roughly 3 billion years of life on Earth that left almost nothing countable behind. Which means the entire apparatus of ranking mass extinctions applies only to the sliver of time in which the record is good enough to support the arithmetic. Something very large may well have happened before it. Something very large almost certainly did. Around 2.5 billion years ago, free oxygen began accumulating in an atmosphere that had never contained any, and for the organisms living then, every one of which had evolved in its absence, oxygen was a poison. That transition was very likely the greatest reorganization of life this planet has undergone. It appears on no list of 5, and it never will, because there is no fossil record fine enough to say what it removed. So what can actually be said with the reckoning done? 5 large drops in marine diversity exist in the record. They are real, they are the largest since the early Ordovician, and every one of them was an enormous physical event with a mechanism that can be reconstructed in some detail. The end-Permian is first on more of the available measures than any other, and never falls below second on any of them, which makes it the closest thing to a stable answer this subject produces. There is a common thread. 4 of the 5 involved a large and geologically fast perturbation of the carbon cycle, arriving from different directions, drawn down by weathering in one case, released from cooked sediment in another, released from mantle magma in a third. The 5th killed by removing sunlight, which is an attack on the same system by other means, since the carbon cycle is fundamentally a matter of what photosynthesis fixes and what decay releases. There is also a shorter list than one might expect of ways to break a biosphere. Heat, oxygen loss, hydrogen sulfide, dissolved carbon dioxide in the blood and in the water, acidification, the loss of light. That is close to the whole inventory, repeated in different combinations, at different speeds, across 400 million years. And a flood basalt province is implicated in all 5. Confirmed in 2, argued in 3, which is either the single most important pattern in the field or the most persistent case of looking for the keys under the streetlight, because flood basalts are large and obvious and easy to date, and there is no comparable way to detect the absence of one. Against that, here is what remains open. Nobody can say what actually triggered the Ordovician glaciation, and there is a serious published position holding that the glaciation was not the killer at all. Nobody can say how long the Devonian crisis lasted, within a factor of 50. Nobody can say which of the 4 simultaneous mechanisms did the most damage at the end of the Permian, or account confidently for why the land died 100,000 years or more after the sea. Nobody will state a magnitude for the end-Triassic. And at the end of the Cretaceous, 45 years after the iridium was measured, it is still not settled whether the volcanism contributed materially or arrived too late, or whether the animals that died were already declining before anything hit them. The category itself is in no better condition. The statistical claim that made the Big Five a category was overturned within a year of being published, and the phrase survived because it was convenient rather than because it was defended. There is a reasonable argument for a 6th, the Capetanian crisis, around 259.8 million years ago, associated with the Emetian volcanic province in southwestern China, which some workers hold to be comparable in genera lost and in ecological consequence. There is an equally reasonable argument that the number could be 12. The choice of 5 is a decision about vocabulary that hardened into a fact, all of which bears on the question that anyone thinking about this subject arrives at eventually, and it bears on it in a way that is worth being precise about. The paleontological definition requires the loss of more than 3/4 of species within a geologically brief interval, conventionally taken as under 2 million years. In 2011, Anthony Barnoski and colleagues worked out what the present rate implies against that standard. If every species currently assessed as threatened were to go extinct within the next century, and if that rate then continued unchanged, the 75% threshold would be reached in something like 240 to 540 years for the vertebrate groups that have been fully assessed. Both of those conditions are carrying enormous weight, and the authors said so. A review published in 2025 points out that the time frame is genuinely unclear and that other projections put the same threshold thousands of years away. But the deeper problem is structural, and it is the reason this account cannot give you an answer. Every method used to rank the other 5 requires the event to be over. Subtracting background extinction requires a stable baseline on both sides of the crisis, before and after. Ranking by ecological severity requires knowing what the rebuilt ecosystem looked like. Ranking by rate requires a duration, and a duration requires an end. Ranking by recovery is self-evidently retrospective. Ranking by permanence requires waiting long enough to find out what never came back, which for the Devonian meant waiting 100 million years. We are inside the interval. The interval is the thing being measured. Every instrument in the toolkit is a retrospective instrument, and there is no version of it that can be turned around and pointed forward. Charles Marshall, at the end of his review, suggests that the current situation might more accurately be called an incipient mass extinction rather than the 6th one, and that is a statement about measurement rather than about anything else. It is where the evidence leaves the matter, and it is where I will leave it. Worth adding, flatly and without any implication attached, there will be more of these. That is not a prediction about anything human. It is a description of a planet that still has a molten interior, still assembles and disperses its continents, and still shares its orbit with a great deal of loose material. Whatever the current interval turns out to be, it will not be the last one. What came through each time is the part of this that keeps its shape across all 5. After the Ordovician shelves refilled with bad water, it was a handful of cold-tolerant brachiopods, undemanding, occupying every continental shelf on Earth at once. After the Devonian, it was a very small number of fish and 4-limbed lineages that spent the next 15 million years being rare. After the Permian, it was whatever could hold its own internal chemistry steady, while the water outside it went wrong. Animals with gills and pumps, and on land, animals that could get underground. After the Triassic, it was the ones that were already cold. After the Cretaceous, it was the small, the burrowing, the freshwater, and the dormant. None of them were the dominant animals of their world. Not one. In every case, the groups that had been running the place, the reef builders, the armored fish, the heavily calcified invertebrates, the large land predators, the animals that had held the top of the food chain for tens of millions of years, went down, and something unremarkable carried on. And the trait they share is not resilience in any admirable sense. It is low requirement, not needing much food, not needing a particular temperature, not needing a specific habitat or a stable one, or one that produced fresh food every morning. What survived 5 times running was whatever could go longest on the least, which recasts the image this whole subject rests on. The long winters, the dimmed skies after the biggest events, the years or millennia of reduced light and stalled photosynthesis and biology running at a trickle, are not simply the worst part of the catastrophe. They are the mechanism that does the choosing. A world with the lights turned down does not kill at random. It sorts very precisely by how much a thing needs, and it has run that sorting 5 times, and it has come back with the same kind of answer every time. There is a version of this that gets told as reassurance, and it is not one I can offer. The 5 recoveries took between about 5 million and something over 100 million years, and no living thing experienced any of them. The Earth did not bounce back, because bouncing implies a shape it was trying to return to, and there is no evidence of any such thing. What happened is that the physics permitted a new configuration and the survivors filled it, and the filling took so long that the word recovery is a courtesy we extend from a great distance. The 5 corridors do converge here. That is not a purpose. Nothing was aimed at anything. It is simply that a chain which has never broken has, by definition, a current end, and the current end of this one is a warm animal lying down in a room at night, on a planet that has emptied itself 5 times and refilled 5 times without any particular regard for the outcome. You are not what the survivals were for, you are where they have reached so far, and the calm available in that is a specific one. The planet's time is not consoling. It is not threatening either. It has no opinion at all. It is simply longer than any calendar can hold, and deep enough that everything in this account, all 5 events and every recovery between them, fits inside a 1/10 of it. You are sitting inside that duration right now. The lines are still in the rock in all the places they have always been. A gorge in central Italy, a quarry in eastern China, a hillside in southern Scotland, cores in boxes in North Dakota, on shelves, in the dark. You could go and put a hand on one. People do. This is one of the quieter stretches. The last of the 5 is 66 million years behind us, which is a long time by any measure that matters to anything alive. The continents are drifting a few centimeters a year. The carbon cycle is turning over. Somewhere under the ocean floor, new crust is being made. None of that requires anything from you tonight. The planet has been doing this for 4.5 billion years, and it will go on doing it, slowly, in the dark, whether or not anyone is watching. Let it rest now.